And he'll be presenting on building modeling libraries with Dyad.
Hi, I'm Venkatesh Prasad Bhatt, and I'm here to present building Dyad libraries. So I would like to say what Dyad is, how do you install it, and what standard libraries Dyad comes with, and how you can create your own Dyad library, and how you can add a custom component to it, and you can add analysis to it. So Dyad is a modeling system for next generation of engineers. So it adds all the latest differential programming and then scientific machine learning, Gen AI, with all the traditional modeling systems like acausal physical modeling and control analysis, all those things. The good thing about Dyad is it follows a single artifact philosophy, that is, a single file. You'll be able to both represent the same model in GUI and also in the textual environment. And Dyad leverages the Julia's ecosystem, so all the goodness of package manager, test-driven development, CI/CD, all those things are also bundled in, and it composes very well with all the Julia, packages, especially the SciML ones, which really gives a lot of power to your models. To install Dyad, you have to create a Julia Hub account at that URL, and you also have a Dyad Studio extension that is available on VS Code marketplace. Once you install these two, you can use PKG authentication to install juliahub.com package server. And once you do registry.add, it adds a registry called Dyad registry. So this is one stop for all things Dyad. It provides all the standard component libraries and also analysis libraries and a lot of helper packages to manage data in the Dyad world. So a brief overview on Dyad libraries. We are trying to build a very rich ecosystem around this Dyad. We have several component domains, electrical, translational, rotational. We have already covered 5 domains, and we are planning to cover almost all the domains in Modelica standard library and also add a lot more in HVAC, batteries, and more. And all these libraries are modular and lightweight. So you can add just the library that you want. Like any other Julia package, you can just do a pkg.add, and only those components are available in your environment. And then there are also analysis libraries. So for control systems or surrogates or model optimization or even the FMU generation, these analysis libraries go very well with rest of the Dyad component libraries, making it a very powerful toolkit. To create your own library using the Dyad Studio, you hit the command pane and you can create component library and provide a library name and path. It does several things for you. So it creates a template Julia package that looks like a standard Julia package with a module file, a test file, a project toml, and also it enhances that with a Dyad folder. So inside this Dyad folder, you have all the components that you define. And when you hit Dyad compile, all the code is generated, and that's placed in generated directory, and that is included within the Julia module. And the assets folder is where all your logos and etc. you can keep, so that the visual representation part can leverage those logos. If you look at Project Toml, there is one package called Dyad Ecosystem Dependencies. I already mentioned that these packages are supposed to be very modular. So how do you maintain compatibility across component libraries? That's where Dyad Ecosystem Dependencies comes in. So this pins to a particular version. Under the hood, it is pinning like around 300 packages. That is modeling toolkit, ordinary DiffyQ, all these SciML packages, without which, without pinning all those things, it would be a nightmare to handle all these different component libraries. So all you have to worry about is that one package and which version that is. And just by controlling that, you can kind of keep all these component libraries in sync. To build your own component library, Dyad is an acausal modeling framework. So we have a lot of standard libraries. You can just add them to your environment and access them. I'm building a piezo harvester here, which has translational and electrical side of it. I'm adding mass, spring, and damper system. Under the hood, it is figuring out what a mass is and does it have a flange, what are the parameters, are you providing the right input. All those heavy lifting is done by the dyad compiler, and if something fails, it gives you, once you run compile, it gives you an error or a warning saying that, okay, something is missing or something needs to change, and you can fix up based on that. And then you can also add other domains like electrical domain. I'm completing the electrical circuit part of this, where this is a capacitor and a load and a voltage source. And then I'm adding the parameters and completing the initial equations and rest of the relations. Here, if you notice, dyad already has some of the SI units defined. But if you need more than that, you can even define custom type and specify that, OK, this parameter is of this type. All these help in document generation and also unit balancing. And then you add metadata. Dyad, this is where, for GUI, representing in GUI, you can specify the XY coordinates and the logo and how the connection should look like and everything. And once you specify all that, Dyad builds up a visual representation for that. You don't have to worry about where the assets are. In whichever dependency the logo is, it pulls in correctly and puts it in right places. To complete this component, you're not just defining a component, you're also, you can also define analysis for these components in Dyad. Dyad provides steady state analysis and transient analysis out of the box, which is part of, you can just define a transient analysis and it takes a set of arguments. And then when you run this analysis, it is building that model, structurally simplifying it, and building the component for you and giving out the results back. It is building an ODE problem and also giving the final result. So for plotting, etc., it's very convenient that you just run one analysis and then you just analyze that. You can even specify your custom plots if there is a particular model and it should be visualized in a particular way. You can even specify that, and the user will only have to run that analysis and then plot, and everything just works. Yeah. If you guys are interested in hands-on session, there is one at 12 o'clock. You need to RSVP for that. This is the link. It is a lunch and learn session for Dyad. Yeah.
I should say that's on the schedule as well. So
Yeah.
Thank you very much. Good job. We have time for one or two questions, if anyone has one. OK. You have a question?
I just wanted to get
Oh, hold on. Let me.
Yeah, I'm trying to locate where you can locate the template for creating a new component. There you go.
Yeah.
I just need to stare at this for a sec.
Yeah. Yeah, the commands are, you just hit the create component library and it does that for you. Yeah.
OK, very nice. Thank you very much for your time. And can the next speaker please come up and
Thank
plug
you.
in their computer?
where's the HDMI? Ah, here. Thanks. Screen. Yes. Okay, and this should be.
Great. So we'll let the next speaker introduce himself and the topic, and he'll be giving the next two presentations.
All right. Hey, folks. So this is now the Climate Science Mini Symposium, I suppose. So just out of curiosity, as a show of hands, how many of you folks are familiar with geospatial stuff or do geospatial processing? OK, sweet. So a couple of people. Okay, so I'll sort of start from the basics here. This is mainly going. These next two presentations are mainly going to be using the Julia Geo ecosystem. Well, I guess I should introduce myself first. So I'm Anshul. I work at Julia Hub now, but I do a bunch of geospatial processing stuff as well. I'm the author of geomarchy.jl. I do a bunch of stuff with the marquee plotting library. And yeah, so today I really mostly just wanted to give an update on this geometry ops library, which is a sort of initially intended to be a grab bag of random geometry processing utilities, right? So geometry being, maybe you have a couple of points on the earth, you have some lines, you have some polygons, things like that. So I'm not going into the full 3D CAD meshing kind of thing, right? That other people have done that in Julia to quite some success. And so this is mainly 2.5 dimensional stuff. And so the reason that I'm emphasizing the sphere here is because we do happen to live on an approximately spherical object. And many people have tried to make that spherical object a planar object, and that always comes with some trade-offs. But you can also perform computations on the sphere itself, right? You can just use 3-dimensional coordinates on a unit sphere, and that gives you a lot more accuracy for some things, right? In some crazy edge cases, you may even want to compute directly on the ellipsoid that is the Earth, or the ellipsoid that is something else. So you may want to find the area of a crater on an asteroid, for example, which is some crazy oblate ellipsoid or something. So there's lots of stuff that comes with, there's lots of nonlinearities and fun stuff that comes with spherical processing. So what is geometry ops? What is this thing, first of all, right? It's a grab bag of geometry processing tools. So geointerface.jl is sort of the central package. It's an interface for geometry that defines how you can access a geometry and defines how you can convert one form of geometry to another, right? And so the idea is you can say, most ecosystems have a single geometry representation, right? You read something from a file, you read it from a JSON or from a binary or from shapefile or something, if you guys are familiar with that. And those all save in different formats, right? And with different memory layouts. But at the end of the day, in most ecosystems, R, C++, Python, right? You convert into one representation. Of course, this being Julia, we weren't happy with that. And so what GeoInterface allows you to do is to use any in-memory representation of geometry, and you can do all sorts of crazy tricks, right? Like you can interleave your points, you can have like 3 different vectors, you can do all sorts of crap. But the idea is that you just have one consistent interface to access those. And you can convert from one form to another, so this is really useful for if you want to write a file, for example, right? You can just, all the writers just work on any geointerface geometry. And so we're able to call out to all of these random C libraries that have had decades and decades and decades of work. But then if you want a different algorithm, you can also just write it in Julia or call out to a pre-existing Julia implementation. So yeah, geometry ops was meant to be the grab bag for those sorts of algorithms. Any geointerface compatible input works, so that's stuff from stuff read from files, stuff that you created in memory, stuff that you got from a database. Some of its capabilities are you can do geometry clipping and intersection, right? So what's the intersection of these two polygons? Do they intersect in the first place? Do they only touch each other at one point? Do they touch each other on a line? Right, things like that. You can do interpolation within a geometry, or so if the border of your polygon has some value associated with it, right? And that's actually a flawed version of that interpolation algorithm is how I got this logo. So I think I had an off by 1 error in the indexing, so it ended up doing that. But you can manipulate coordinate systems, so you can go from one coordinate reference system to another. But the really cool thing that a lot of this is built on is this framework to automatically decompose geometry, right? So going all the way from a table with associated attributes, right? So you could have like countries, which could be polygons, could be multi-polygons, right? So a single polygon is just an exterior and a bunch of holes, but it has to be contiguous. A multi-polygon can have, for example, well, Pennsylvania doesn't have any islands, so that's probably a bad metaphor. But it could have, for example, a country and some islands associated with it, right? And those islands do not touch the country at all. They're completely separate. So this gets really painful because all of these structures are different things, right? Like you could even have completely different things. You could have a data frame with polygons, with multi-polygons, with lines, with multi-lines, right, with points. And so let's say you wanted to project those from latitude, longitude to a different map projection, right, for example. If you tried to do that yourself, well, you would have to see, okay, is this a multi-polygon? If so, then decompose to polygons and call the polygon routine. Okay, is this a line? Okay, decompose to points and call the point routine, right? And so what this apply and apply reduce framework does is it lets you specify a target geometry type that you want to accept, and then anything you pass in, if you pass in a vector, that each element of that gets decomposed, and whatever the result is from apply gets reconstructed and put back into a new vector, right? If you pass in a table, you maintain all the attributes and things like that. So this is a really a pretty cool framework. And if there's interest or time, which I'm already running short on, I can show some code examples. But some of the new stuff that we've got is tree optimizations in geometry ops. So you can accelerate a lot of your intersection computations by basically grouping geometries into sort of areas, right, and building up trees on that. And so generally people call these spatial trees R trees. If you're familiar with databases, you might have heard of R trees or B trees, right? But the cool thing about having this in Julia is I can experiment with any implementation. And so I can also not necessarily have trees with rectangular bounding boxes. So someone in the Max Planck Institute in Jena is using this interface that we've developed to use trees with basically caps on a sphere, right? So you have a point and some spherical angle around that, and that defines a region on a sphere. And so that becomes your bounding box of your geometry. So I don't know if this video will show particularly well, but this is building up a classical R tree on a circle, right? And so you'll notice that it's pretty deep because the node capacity was only 10, but each of these, this is where it gets iffy to show. But each of these boxes, so the green boxes are a lower level, the orange boxes are a higher level, the blue boxes will be the highest level. And so you can see that this sort of builds this up in this arbitrary order, right? But there's this other algorithm which someone had implemented in a C library called natural indexing, where you basically say, okay, let's say I have a polygon, right? If I go from vertex I to vertex I plus 1, those will generally be sort of correlated, like they'll kind of be pretty close to each other. And so I don't actually have to waste time sorting all my points and binning them into an R tree. I can just walk along this polygon, and every endpoints, I create a new box. And so this is a natural tree on a circle. You can see that it's got a lot less layers, but it's got about the same amount of spatial fidelity. But the cool thing is if you do that on a complex geometry, so this is the state of Texas. This had about 7,000 points, I think, from memory. I kind of simplified it a bit. And so you can see that, okay, over here, this is one of the disadvantages of this tree, because this is basically 1 point, 1 point, and then 1 point, right? And so that whole spatial area kind of gets eaten up into one node. But if I go and look at the STR tree, there we go. If I go and look at the STR tree implementation, what happens is that So each of these has certain advantages and certain disadvantages, right? And if I forward this a bit, you will see that this tends to build up these very, very large nodes that have a very, very large Y span because it's sorting in X. And so this is actually a much less optimal tree to query on than the previous one for some cases. And so you can keep doing this crap. There's also a new interface for these things called manifolds. So this is kind of where the spherical stuff comes in. So most geometry processing algorithms will be kind of similar, will have kind of similar implementations and kind of similar ideas behind them, no matter if you're doing it on a plane, a sphere, or an ellipsoid, right? So let's suppose you wanted to calculate the area of a polygon or the length of a line. Well, I mean, conceptually, that's simple enough. It has the same input. You have the same parameters if there are any. But what space are you computing this on? So the default thing that everyone does is just, you assume it's on a plane, right? If you try to compute the area of the US based on a regular just shoelace area formula, you will get a completely nonsensical answer because you're just computing it in latitude and longitude. If you try and project to some optimal coordinate space, Okay, you'll still have spherical warping, you'll still have this, you'll still have that, right? But with this stuff, you can specify, okay, I want to compute this on a plane. No, no, I want to compute this on a sphere. No, 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 I want you to compute this on this particular ellipsoid, right? And so geometry operations can just look at the manifold that you have defined and dispatch on that. So there's a new, to build on top of that manifold thing, there's a new algorithm interface as well, right? So you can store the manifold and several parameters in this algorithm by which you compute or by which you perform some operation. And where this really gets interesting is with polygon intersections and tree acceleration for those. Because you can say, okay, you know, I know that my polygons are pretty weird, so I want to go with the safe option. I want to have an STR tree, and I want to bin all the lines into this tree structure and make it really fast to find which lines intersect which other lines, right? Or for example, there are multiple ways to calculate the area of a polygon on a sphere, right? And so which one do you want to choose? Well, you can just choose any of them. The developer doesn't have to make that decision. You as the user have the freedom to do that. So yeah, I think I'm probably a bit over time on this. But yeah, any questions so far? No. Ah,
Hi, very cool. You mentioned that you can that it works on data sets that come from any source that you have in memory. So if you have like a large mess, millions of cells that was exported in like an NK gold file,
I don't think
would you be able to import that?
I don't think I have ever encountered those. So we probably didn't write a function, library to import them. But if you
Okay.
can import them into Julia, then yeah, absolutely. You can just represent them.
I've been able to import them into VTK based library in PyVista in particular with Python. Maybe a solution if PyVista is able to export it to something you can
Oh,
use,
sure.
we can
Yeah,
we
yeah,
may
yeah.
just do the PyCall method and
Yeah, yeah, yeah,
wrap it that way.
absolutely. That would be very possible, yeah.
Okay.
And the cool thing with GeoInterface is you could actually define the GeoInterface methods on your Python object.
Okay.
So you could just directly use that and access those, right? Or you pull it to Julia or something, but yeah,
Okay.
that's also an option. Cool. All right, let me see here. I may have to do this. Oops. Sorry, just have to log into this other thing because I made this in PowerPoint. All right, so let's see here, slideshow from the beginning. Okay, so this is a project I did while I was at NASA's Jet Propulsion Lab. I was doing an internship there, and the whole problem is that modern Earth observation data sets, right, the images you get from satellites, they will have sizes from a terabyte to a petabyte, and they're only getting bigger. So this is obviously not very conducive to in-memory processing. But what if you want to use these, and you know, people have solved this problem mostly for very large queries on very large data sets, right? If you want to process this entire data set, there are many ways to do it. You can go to Python, you can use Dask, you can launch off 500 jobs using Coil, right? You can use distributed in Dagger.jl and Julia. So there's lots of solutions if you want to run a statistic over the entire data set. But what if I have this gigantic data set and I want to answer a lot of very small questions? So for example, let's say I have a data set of the mean temperature of, you know, every 50 meter by 50 meter pixel of the world. And I want to find the mean temperature for every US county over time. That's a lot of counties. If you take their bounding boxes, they overlap a lot, especially in the East Coast, right? And they don't fit meaningfully in the way that this data set has been pre-chunked for you. So a big question that we had was, you know, how do you actually deal with this? How do you take these very, very disparate, they could be spread out, they could be close together, but how do you take these very disparate areas, load them into memory, and do some processing on them from this giant data set? And so here's just a visualization of all the counties of the US, right? It's pretty big. Conventional wisdom would say download only the parts of the data set you need. That's fine, but it's manual. It takes a while. And generally, you just take the bounding box of all of your data and you download that, but the bounding box spans the globe. What are you going to do? So one option is you could say, okay, for each individual polygon, let me take the bounding box of each individual polygon and download that, right? And let's say my server can handle this. But you repeat the downloads of that data a lot. And this package rangeExtractor.jl is designed to take the headache out of this. You batch the downloads based on what polygons intersect what chunks of the data set. And I'll go over what data set chunks are now. So at the end of the day, any data set you have is a vector of bytes, right? That's how it's represented on the disk. Storing a single 1 terabyte vector of bytes is generally understood by most people to be a bad idea. And so what people have come up with is you break this up into chunks, right? So these chunks are basically rectangles in n dimensions, and the size of the chunk dictates the optimal form of data access. And what that means will become clear in a sec. But chunking lets you download only the data you want. Too many chunks means if you have very, very small chunks, you have to make a lot of HTTP requests if your data is on a cloud, right? And so that's a bottleneck. But too few chunks means that whatever you will download a lot more data than you generally would need. So it's kind of a balancing act. Let's say we have this Earth data set, right? This is the entire Earth. You could chunk it up like this. And so with this, what happens is you have a lot of spatial grouping, right? So if you wanted to get all the data for Brazil, well, you need this one, you need this one, and you need that one, right? But you only need 3 chunks out of this gigantic data set. You don't need to download the full thing. But you could also chunk it this way. Let's say that I want to get the average temperature of the Earth at each line of latitude. In that case, this is actually great, because first I can get that top chunk. I run my computation on all the lines of that top chunk, right? Ideally, that fits into memory. Then I go to the next chunk, I compute that. But if I wanted to get the data for Brazil, which is over here, then I have to get these 2 gigantic things. So this is the trade-off that you face. And chunking is, of course, not restricted to 2 dimensions, right? Let's say I have a data set where I really, really care about local time series. So I really, really care about taking this one latitude, longitude point and going back from 2025 to 1980, right? Then you would chunk like this, where you have a long time dimension, but very small spatial dimensions. Or let's say that I have a data set where I only really care about one point in time, but I care about a lot of points in space, right? I want to analyze, I can't actually think of a good example right now. But yeah, okay, something like forest cover in June of every year, right? So you only care about one point in time at a time, but you care about the whole spatial area. And so then you have very thin chunks in time, but very wide chunks in space. And so this is a nice representation from Czar of how these chunks work in memory and how you load them. And so basically, each chunk has an address. And this library was in Python. And so you would sort of have this zero-based indexing. And each chunk has an address. It goes through filters, which can make the data more amenable to compression, right? For example, you might say, okay, take my data and scale it by this amount and offset it by this amount such that it goes, such that it goes from 0 to 1, right? And then you can reverse that operation when you load it. So the idea is you have these ranges that define views into the array that you want to load. You have some metadata which go with each range, so these ranges are just indices. And you have a tiling strategy, which is the way you choose to, the way that your data is tiled, effectively. And then there's some operation that you want to execute on that. And at some point, I haven't implemented this yet, but at some point you want to also optimize the execution order so that you don't load too much stuff into memory at once, right? Tiles which are adjacent to each other would sort of get loaded one after another, and so then you can discard the whole lot after you're done. So let's say I have this data set. Let's say this is the broad area which I care about. This is the bounding box of all the polygons that I care about. Right, and so let's say I cared about the US, the contiguous continental US here. What I can do is, let's say my data set is tiled like this, right? And so what you do is you would first load one of these, you run your processing. Then you load this guy, you run your processing, right? And so you go so on and so forth. You've loaded everything, you've run your processing, and then you run some reducing operation, right? And so let's say I want to take the sum of all values in this polygon. Well, what I can do is I can just take the sum of each individual tile and then sum all those at the end, right? That's a simplistic example, but there's lots more stuff you can get up to. You can sum the histogram over some dimension or something like that. The really cool thing is when you have this kind of stuff. So you have these bunch of states, right? Some of these cross the tile line, some of them don't. But you don't need to load this thing, 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 right? You only need to load the tiles which you explicitly need. And so, this is what it would look like if you zoom out. And yeah, so the main concept here was this idea of like a range which is contained within one tile versus a range which is shared between both tiles and how you handle that. But I think I've run out of time, so we'll cut that here. But yeah, thank you.
Thank you very much. Really good job. While our next speaker plugs in her computer, we have time for one quick question, if anyone has it. Okay, well, thank you very much. That was a great presentation. And let's get going. With the next speaker, we'll let her introduce herself and the topic.
Yeah, good morning, everyone. Yeah, I'm Karishma, and I'm here to, I'm a cloud DevOps engineer, and I recently started exploring scientific machine learning, and I have done a project related to modeling the ocean pollutant dispersal, and I'm part of the team who guided me and who helped me in this research project. So my team is from like Visuara AI Labs, who have helped me into understanding and dig deep into the problem statement and how effectively we can model a solution for the research work that we have started on. So our journey over the past year hasn't just been about building a single model, but we have focused more on understanding how we can build the models well. So I'm going to explain how we have used Julia and its scientific machine learning ecosystem to conduct a systematic investigation on how to find a robust and reliable method to when applying physics-informed neural networks to complex fluid dynamic problems. Yeah, so I would like to start with the problem that we have picked upon, and which is ocean pollutant dispersal. So I would like to explain the scale of the problem that we have initially looked at and how we could improve the traditional methodologies on how we deal with the pollutant spreading across the oceans. So an estimated like 8 to 11 metric tons of pollutant plastic is being dumped into the oceans every single year, and this has been growing every year. And what we wanted to do is have a systematic use physics informed neural networks to model the underlying dynamics when we deal with a pollutant involving like fluid mechanisms. So what you're seeing here is a picture showing a major surface currents of North Pacific. So these large rotating systems are called ocean gyres. So we can think of it as a slow moving whirlpools that span across thousands of kilometers. And they act like massive conveyor belts collecting the debris from the coastlines, and they slowly pull the debris from towards a calm and like a stable center. And as a result of this accumulation is what we see in the next picture where I have showed, it's like a Great Pacific garbage patch. So it's not just like a solid island of trash that is present, but it's a diffuse of microplastics and all the other debris that gets collected on the ocean. So the largest of these patches is estimated to be over 1.6 million square kilometers. So this brings us to the core scientific challenge. So how can we predict or understand how they drift and grow or break apart over the time? So we need to accurately model the underlying physics for it, and this is a very complex and large scale fluid dynamics problem. And where we hit the wall with traditional methods is like simulating these vast domains at a high resolution for decades of time is often slow and computationally expensive. So that's why we kind of tried to experiment on how we can come up with a method that's both physics aware and also data efficient. So that's where we thought like physics informed neural networks can kind of help in having a better way to integrate this. And we believe that the physics informed neural networks offer a more powerful and physics aware and ultimately more computationally friendly and useful way to model this, understanding the underlying physics of it. So a physics informed neural network is basically it considers the experimental data like a general normal neural network, but it is also forced to obey the physics laws that we and govern the equation and consider that in the laws that we build across the neural network. So so why did we use it mostly as a way is important thing that we have considered physics informed neural network is that it allows us to embed physics laws. So unlike a standard neural network that might only learn statistical correlations from the data, physics informed neural network integrates our knowledge into the system. So in this case, we have defined a partial differential equation, and we can govern this equation directly into the training process. So this acts as a powerful regularization and ensures that the solution are physically consistent. So the model learns the rules of the system and not just the patterns that we provide in the data. So, and also they are mesh free, they don't require a complex or often process of creating a computational grid. So this makes them incredibly useful for handling like irregular geometries like a coastal line or without any hassle. So the network learns a continuous solution over the entire domain, and which can be evaluated at any point in space and time. So, and also we understand that physics informed neural networks are very good with data integration, so they can learn from sparse or noisy data. And this is exactly the challenge where this is exactly what we get from the real world environmental sensors. So they can effectively fill in the gaps between measurements using the underlying physics as the guide. So I think all of these advantages combined will make a powerful tool for the data assimilation and also solve inverse problems. And I would like to explain about how a physics informed neural network works and how we designed the architecture like the existing to the existing problem that we have picked up. So basically it's the iterative process of prediction and correction that combines the learning with physics. So we start with our inputs and constants. So in our case, it's time, t, and spatial coordinates, x and y, and physical parameters. So these are directly fed into the physics-informed neural network. And the network, which in our case is a 9-layer 128 neuron network with a tanh activation function. So it processes these inputs and it makes a prediction of the pollutant concentration at that point. And this prediction is then evaluated by a composite loss function. So we use automatic differentiation to calculate the PDE residual, so which forms the like the physics laws. And this is where is the main point where we are checking the network's output against the governing physics equation itself. So we also compare the prediction to our reference data, so which gives us the data loss and heavily weighted initial condition loss. So these three components combined into a total loss, so which we have which we have composited like a total loss with the equation, and this single number tells us how wrong the network currently is, and we used the optimizer Adam which uses this loss to calculate the gradients and update the network parameters. So the entire loop repeats multiple times, where each iteration nudging the network closer to the solution that respects the data as well as the physics, and it overall at the end, like until we get the output which becomes a highly trained surrogate model. And so I'll explain the specific equation that we are embedding. So our system is governed by the 2D advection diffusion equation. So this equation is made models two key processes. So the advection term describes how pollutants are transported or carried out by the bulk motion of the currents, and the diffusion term describes how they spread out from a high concentration to a low concentration region due to maybe random molecular motion. So this is the fundamental equation for transport phenomena, and I'll let's take a closer look at the first key physical process in our equation, which is advection. So at its core, the advection is simply the transport of substance by the bulk motion of the fluid. So here the object which is moving within the fluid, the water's movement is transporting it from one place to other place for the object. So mathematically we represent this term, if you see a product of velocity and delta u. So here it represents the v represents the vector which is a velocity of the ocean current. So it shows how fast or in what direction the flow is and the water is moving, and delta u is the gradient of the pollutant concentration. So it tells us how the concentration changes in space, essentially the slope of our pollutant peak. So when we expand this into our 2D model, we get the expression which simply says the total transport, that is the sum of transport in the both directions x and y, and so the plot gives us a visual of how the concentration field might look like at a specific moment of time. So overall advection is a process that would take this entire peak and move it across the domain following the direction of the current. And the second key process that governs this is diffusion. So it's basically where the substance spreads from a high concentration to a low concentration area driven by random molecular motion. So mathematically this is captured by the term product of a constant diffusion coefficient and delta square u. So here it is the diffusion coefficient is what quantifies on how quickly the pollutant spreads. So a higher value of diffusion coefficient would mean a faster and a more aggressive spreading. And the delta square u is the Laplacian. So we can think of it as a measure of the peakness or the curvature of the concentration. So the sharper the peak of the pollutant, the stronger the diffusion effect will be at that point. So this is simply a expansion of the Laplacian in our 2D coordinates, and we have used specific constants for the velocity and the diffusion coefficient for our experimentation. And yeah, so as we looked at the two core physical processes, so this defines a complete well-posed mathematical problem that we are asking our physics-informed neural network to solve. So you see the full 2D advection diffusion equation where this is the fundamental law of physics that our solution must satisfy at every single point in space and time within our simulation domain. So, but the PDE alone isn't enough to give us a single unique solution. So we also need to provide it the context. That means describe the specific environment of our simulation. So we do this with boundary conditions and initial condition. So we have set a boundary condition for our study where we used a Dirichlet boundary condition. So which means that we are specifying the value of the pollutant concentration at the edges of the domain. So as you can see, like we have set the concentration to be approximately 0 at all the 4 boundaries. So this setup simulates a localized like pollution event happening in the middle of like much larger body of water. So and also the small epsilon term represents a slight noise or measurement uncertainty that we would expect in the real world sensor reading. And coming to the initial condition, this defines the state of the system at the very beginning of the simulation. So initial condition. So we have defined this with Gaussian function, which is like a sharp localized peak of the pollutant standard and effective way to model this. And so the complete task of for our physics-informed neural network is not just to learn from any function that satisfies the main PDE, but it's to find one specific solution that also respects these exact boundary and initial conditions. So this is like a complete well-posed problem that we have set out to solve. And yeah, so to implement all of this, we have built our framework in Julia. We have used quite a few libraries which has been a massive accelerator for our research. So we used Neural PDE library to symbolically define our PDE system. And this is an incredible feature for random prototyping and also avoiding the manual or error-prone process of implementing like complex discretization. And we could literally write down the math and the library would construct the loss function. The Lux library has provided the flexibility and explicit parameter handling that we needed to define our neural network architecture. And this was crucial for our systematic investigation. And so also the optimization package gave us like unified interface for driving the training process with different algorithms. We have tried it with different optimizers, ADAM-W, and the second order methods like limited memory, BFGS, to test the performance. And we have effectively also used plots and benchmark tools libraries to analyze our results and also measuring the performance with high precision. So the ability of all of these specialized tools to work together seamlessly is what helped us to effectively understand and experiment different scenarios. And we have utilized the strengths of Julia and the libraries wherever we wanted to in the experimentation process. So, so with this toolkit, we designed a series of controlled experiments to find the best possible model. So first we needed ground truth to train against. So we generated our reference data using a traditional finite difference method on a 51 by 51 grid. So the process was fast, and also we then added a small amount of Gaussian noise to this data to simulate this kind of imperfect measurements that we would get from the sensors in like the realistic data. So with the problem defined, we have arrived at the core of our investigation, which is like finding the optimal set of hyperparameters for our physics-informed neural network. So the goal wasn't just to pick some numbers that worked, but to conduct a systematic search of the design space. So we looked at the network depth and we tested with initially 5, 7, 9 hidden layers. So we started with 5 layers as a reasonable baseline and pushed up to the nine layers to see if a deeper and more complex model could capture the intricate features for the solution. And we focused on line layers as we see that it has consistently performed well. And the most importantly was the network, the neurons that we have tried out. So for each depth, we have tested 64, 128, and 256 neurons, and this range was chosen to test the network's expressive capacity. So 64 was a common starting point, and but we suspected that it would be too small, and we chosen 128 as a middle ground. And also we experimented with 256 to see how if a much larger capacity would yield better results, but or it would be too difficult to train. So, and coming to optimizer, our primary choice was Adam, and we used different versions with tried with Adam, then improvising it with BFGS optimizers. So we wanted to make sure that the standard deep learning optimizers was indeed the best choice for our physics-based problem. And we have tried out with different learning rates and the durations. So we understand, like, the too high the learning rate, it would be very unstable, and also if it is too low, it will take longer to converge. So we tried out different learning rates in this range, and also trained up to 10,000 iterations to ensure that every model was given the cases to learn the solution and reach at a stable minimum in the loss landscape. So this approach is what allowed us to identify the optimal configuration, which I'll show in the results. So after running a few of these experiments, so we have come up to an optimal configuration. So the 9-layer 64 neuron was fast to train, but it consistently lacked the expressive capacity to capture the full dynamics, and it has resulted a higher error of over 18%. And if we consider 9-layer 256 neuron architecture, it was very slow to train, and surprisingly the accuracy was worse compared to the first 64 neuron network, which is like around 22%. And I think this is because the loss landscape is much more complex and non-convex, so making it difficult for the optimizer to find a good solution. So we identified that 9-layer 128 neuron architecture provided the best balance of accuracy and computational cost. So our best run was with this architecture, using a learning rate of 0.06, achieved a final relative error of just 8.25%. So, which is a good result for this kind of a problem. And this, as you can see here, the result of this 64 neuron is the loss history on the right. It struggles to converge and has a lot of noise. And the final prediction on the bottom right is, you can see visible artifacts and noisy background compared to the ground truth. In the 256 neuron network, while its final loss is low, you can see the training was more erratic and large spikes in the loss history. And this is the optimal 128 neuron configuration network, where the loss curve is much more stable and converging smoothly, and the final prediction is clean and visually close to the ground truth from the traditional FDM solver. So this kind of makes us understand that simply having a network bigger isn't answer to the problem or the solution to arrive at a effective and less error configuration. So this is our best configuration that we have experimented, and it has resulted in around 8% of relative error. So apart from accuracy, the other key advantage of physics-informed neural networks is their speeded inference. So the traditional FDM solver can compute a single solution in for our specific problem, it is 0.26 seconds. Training the physics-informed neural network is slow and it's a one-time cost. Our optimal model, which I showed you earlier, it took about 20 minutes to train. So, but once it is trained, our physics-informed neural network became a surrogate model that can generate a new prediction in just 24 milliseconds. So that's more than 10 times faster than the original solver. So this speed is what enables applications like real-time forecasting or large-scale uncertainty quantification studies where thousands of model runs are required. So this is a plot of our best result. So this slide shows like the direct comparison for the winning configuration. So on the top, you can see how a weighted loss strategy allowed the pin to perfectly capture the initial condition, which is part of our methodology. And here on the bottom, you can see the final prediction at the end of simulation, which is remarkably close to the ground truth. So this is how like we could achieve a desired result by combining a systematic search with the right modeling techniques. So our work, what we have identified is it's a physics-informed neural network is a highly efficient tool for modeling complex physics systems like ocean pollution. And also we have identified that the performance is critically dependent on finding the right balance in network architecture, and that engineering the loss function is the key to achieving accurate results. And this is just a foundation that we have started up with, and it's just really the beginning. And our next steps are to extend this framework to a 3D to capture vertical mixing, incorporating real world time variant ocean data, like ocean current data from satellites, and even explore using these models for scenarios like using sensor data to trace a pollutant back in time to find its source. So this is what we have in the roadmap to extend and improve these more, like taking it as a baseline. And yeah, you can find the source code for this project in the GitHub repository, and also a detailed write-up of our methodology and the results are published in our paper on the archive. So you can scan the QR code to access them. And you can also, I'm also open to collaborating into anything that's more in any work with respect to physics-informed neural networks and scientific machine learning in general, and I would be happy to stay in touch and have ideas and thoughts shared. So you can contact me on LinkedIn if to have more to collaborate more on this. And yeah, I think the future of scientific machine learning is bright, and with tools from Julia ecosystem, it's like really building many new things out of it. And I would thank you for the time, and I would be happy to answer any questions or any feedback or any suggestions that you have on this work. Yeah, thanks a lot.
Great job. Thank you for preparing that. We have time for a question if anyone has one. Let's get you in the back first. We should have time for two, so.
Hi, hello. Thank you for a great talk. So I have kind of two related questions, kind of short. How do you decide on the velocities that you chose? And that's, I see that they are constant.
Yeah, there.
And then you mentioned that you want to have like time varying currents. I assume that you want to have that from satellites, but have you thought about like using also the Navier-Stokes equations, right? Because what I think is like when you have the velocity going to the concentration, right, to the pollutant spot, that probably decrease the velocity, and then you will have to take into account to how the motion of the fluid is affected by.
Yeah.
I mean, can you comment on all of
Yeah,
this?
that's right. So currently we started with constant values, and we wanted to add those additional parameters that we want to consider when we deal with like a real ocean currents and other, as you mentioned, like velocity reduces over the time, and those are the parameters that we haven't considered for this initial baseline. And yeah, we would like to explore, dig deep into that aspect. So initially for this as a baseline, we started with the constants, and like we had like a initial constants and the diffusion coefficient, everything is considered for a small grid. And yeah, we would explore more and like improve this more and consider all the variant velocities and all those in the future. Yeah. Thank you.
All right, well, I think it's time for the next speaker, so I'll hand this off to the session chair.
All right, awesome. Thank you, everyone. My name is Jacob Zelko, and we're kicking off the first ever Julia Health Mini Symposium. I'm Julia Health leader, and I'm excited to introduce Kavya Subramanian. I'll let you go ahead and get set up, Kavya, but this will be having a variety of talks today, just as we're going through kind of the mini symposium. So feel free to stay tuned and hopefully learn some about how Julia can be used in a variety of different health research and applications. Thank you.
Good morning, everyone. My name is Kavya, and I am an undergraduate at Boston University. I'm currently a rising junior, and along with the team at Vizora AI Labs, I have been working on an adaptive tumor growth forecasting model via neural and universal ODEs. And today, I'm really excited to share more about my research with you in this talk. So I'll be covering the following. I'll firstly briefly introduce the problem, talk about the motivation behind it, then talk about the existing models that exist, and then dive into the methodology, results, and so forth. So I'd like to begin by talking a bit about the motivation behind this problem. Cancer remains one of the leading causes of death globally, and there's projected to be over 2 million cancer cases and more than 600,000 deaths this year in the US alone. In this context, it becomes incredibly important to accurately predict how a tumor grows over time, as this not only helps doctors to effectively plan treatment, but it ultimately helps in saving lives. And therefore, this problem is not just a theoretical exercise, but rather it has the potential to impact human lives. But let's take a step back for a moment. What makes tumor growth modeling so difficult? What are the challenges? Well, there's several. To begin with, tumors are incredibly complex. There's differences not only across various patients, but also within the cells of the same tumor. So this poses a very, very tough challenge to solve. Besides that, there's the differences in immune system responses when a patient is exposed to radiation or other kinds of therapy. Additionally, we've also got the environmental as well as external factors that influence tumor growth, whether it's the tumor microenvironment, right from the availability of oxygen or nutrients, as well as the surrounding tissue and their stiffness and so forth. Also, environmental factors such as a person's diet or the kind of therapy that they're undergoing can have a huge impact in the way a tumor progresses over time. And from a purely modeling standpoint, there's also the problem of having limited experimental data with very sparse time points. So all of these challenges put together make tumor growth modeling and forecasting a very critical challenge. I'd now like to touch a bit on the existing models for tumor dynamics and forecasting. So firstly, we've got the ordinary differential equation-based models, such as the Gompertz or the Burt-Allenby equations. One big strength is that they're computationally efficient. It's very easy to work with. However, due to the fixed parameters, it makes it really difficult for the model to adapt with patient-specific variability. Similarly, for partial differential equation-based models, although they include that additional spatial resolution, it can still be quite hard to personalize it to a specific patient. And finally, more recently, there have been quite a few machine learning models that have come forth. However, they do lack the biological interpretability of the more mechanistic models, despite being able to capture the more complex nonlinear dynamics of tumor growth. So as you can see, every model has its own strengths and it contributes something important. However, none of them really provides us the interpretability as well as the adaptability that's required for biological modeling. And hence, we would like to propose a scientific machine learning-based approach to tumor growth modeling. Scientific machine learning combines the power of traditional ODEs with the adaptability of neural networks. This allows the model to learn directly from experimental data by replacing fixed parameters with neural networks. So essentially, we're able to retain the mechanistic interpretability of the ODE and PDE models, while at the same time being able to get the flexibility of a pure machine learning model. And therefore, as you can see in the Venn diagram, we get the best of both worlds. All right, so now I would just like to talk a bit about our experiment and the data that we've used. So we chose an experimental data set of breast tumor growth in animal models. These were measurements of tumor volume in cubic millimeters over the time span of a few days. As you can see in the graph, the data followed a sigmoid-like growth pattern, which is very characteristic of typical tumor growth. It starts off kind of slow, and then in the middle, it rapidly accelerates, and finally, it reaches a maximum volume or a carrying capacity where the graph starts to plateau. So in order to get a smooth approximation, we applied a sigmoid-based interpolation to the data, which was able to capture the general trend without fitting to the noise in the data. And then for our base model, we chose the Gompertz ODE equation. It is a sigmoidal growth model that was originally proposed in 1825 to describe human mortality. It wasn't until the 1960s, though, when it was first used to model tumor growth. But since then, it's come a long way and has been widely adopted in both the biological as well as the medical sciences for tumor modeling. And there's several research papers that have assessed the benefits and limitations of the Gompertz ODE as well as a lot of other ODEs. As you can see, the equation mainly has a parameter called the intrinsic growth rate, represented by A, and it's multiplied by the volume as well as the log of the carrying capacity divided by the volume. All right, so we then use the differential equations.jl package to define the ODE problem with the following parameters, and then solved it using the TSIT5 solver. This produced the following result. As you can see, the Gompertz growth is not able to capture the intricacies of the experimental data, and that's where we come in, and we have proposed a neural ODE-based solution, as well as a UDE-based solution. Let's first dive into neural ODEs. What are neural ODEs? Well, they're a family of deep neural network models that replace the fixed parameters in the ODE with a neural network. This allows us to flexibly model continuous time dynamics using a continuous transformation to update the hidden states like so. And essentially, as I mentioned, we replace the fixed ODE parameters with a trainable neural network. We inputted volume as well as time as inputs, and the network has 3 hidden layers with the tanh activation function and the following number of neurons per layer. We also normalized our input data and defined our neural ODE function and subsequently solved it using the TSET5 solver. Finally, we went ahead and optimized our solution using the Atom optimizer. We experimented with a bunch of learning rates and iterations, and the best result was obtained using these parameters. So here is the result of our neural ODE. As you can see, the solution agrees strongly with the experimental data, and it's able to effectively capture the sigmoid-like growth of the tumor, and it's a big, big step ahead from just the traditional Gompertz ODE model. Finally, we took it a step ahead and decided to forecast future tumor growth using our neural ODE model. We started off by training it on 100% of our data, and then forecasted beyond the time span from a range of 32 to 40 days. As you can see, the neural ODE was able to capture that plateauing nature of the tumor growth, and we also went ahead and forecasted with different data ratios. So a train test split of 90-10 as well as 80-20 gave us a really, really good forecast. However, we did notice that at about the 70-30 data split is where there was some deviation from the experimental data. I will be talking about this a little more, but as a next step, we will be performing further hyperparameter tuning in order to reduce this error. Finally, I would like to talk about the universal differential equations. So UDEs combine differential equations with neural networks that allows them to model systems with unknown or partially known dynamics. What makes them different from neural ODEs, though, is that we are replacing just the key interaction terms with neural networks rather than replacing the entire equation. So as you can see here in our example, we are replacing the growth rate A with one neural network and the log term with another neural network. So as I mentioned, we replace the key interaction terms in the ODE, and we feed in the volume and time as input as earlier. Each of the networks has 2 hidden layers with the tanh activation function, and the input data is also normalized to ensure that there's stable training. Finally, we define the UDE function and solve it using the TRBDF2 solver. And we optimized it using the Atom optimizer, but in this case, we had a 3-stage optimization approach with these learning rates. So here are the results for our UDE model. Again, similar to the neural ODE, the UDE was able to capture the sigmoidal growth of the tumor data, and it strongly agreed with the real-world experimental data that we used for training. Then, similar to the neural ODEs again, we forecasted using 100% of our data. And as you can see, it does a decent job of capturing that plateauing nature again. We also forecasted with different data ratios, starting with a 90% training and a 10% forecast. As you can see, the green line overlaps the orange dotted line pretty well. And even at the 80-20 split, it still manages to capture that slowing down pattern. But again, at the 70-30 split is when it started deviating from the data. But we hope to further improve this as this is an ongoing research. We will be performing further hyperparameter tuning to ensure that this result is improved. So our neural ODE and UDE models were able to accurately capture the sigmoidal growth curve of tumor growth, and compared to traditional models like the Gompertz ODE. They were also able to adapt to the nonlinearities in the tumor data by replacing the fixed terms with trainable and flexible neural networks. And finally, our approach also retains interpretability by grounding the neural network in biologically meaningful ODE framework. So this allows us to make inferences from our data, which are grounded in which are backed by scientific meaning. We use several Julia packages in our research, and it significantly helped us model these complex dynamics and made it much easier to work with these complex tools like neural ODEs and UDEs. The differential equations.jl package, the diffeq flux, the optimization.jl, Lux, and so on form the core Julia SciML ecosystem. And we were able to harness its power to make the most of our modeling. I would just like to talk briefly about some of our next steps. As I mentioned, this is still an ongoing research, and we hope to improve our forecasting further by using more hyperparameter tuning techniques. We would also like to determine the forecasting breakdown point for both our neural ODE as well as our UDE model. Also, we only applied this to a specific data set. So in order to evaluate how generalizable our models are, we would like to apply it to more data sets. And also, we intend to make our tools open source after publication and upload all of our code on GitHub. So to conclude, tumor growth is an incredibly complex process, and it's influenced by several factors that makes it a challenge to model and forecast. And traditional models that are based on ODEs or PDEs have limited flexibility because of their fixed parameters. And pure ML models, due to the black box nature of machine learning, don't provide the interpretability that the more mechanistic models have. Hence, we are working at the intersection of both these kinds of models and applying powerful scientific machine learning frameworks, including tools like neural ODEs and UDEs that learn these tumor dynamics directly from experimental data. Our models are not only able to capture the sigmoidal growth pattern of tumors, but they're also able to effectively forecast future growth using just limited data. Finally, to close, I would just like to bring us back to the bigger picture here. Our work shows that by combining scientific machine learning with traditional modeling, we are not only able to improve predictive accuracy, but it also brings us closer to a more data-driven personalization of cancer care. But more importantly, this is not just about a mathematical or a computational exercise. It's a critical tool that helps doctors in decision-making, treatment planning, and also improving patient outcomes. We're taking a step closer to precision medicine, particularly in oncology, and create models that don't just simulate tumor growth, but rather carry the potential to save lives. Thank you so much for listening.
Awesome. Thank you so much. Thank you to our speaker. We have time for plenty of questions right now, so if anyone has any questions, I will run you the microphone. Floor is open.
How many of these curves do you have, like in your? Yeah, I'm sorry. How many of these curves do you have for all the different clients, for all the different patients?
So right now we're using an experimental data set that's based on animal models. So these are mice injected with like tumors.
Okay, okay.
So.
All right, but like how many of these curves, like in your data sets, how many of them are there?
You mean the data points in the
Well,
experimental?
not like, I mean, is it like just one curve that you have, or do you have like many mice that had many cancers?
Yeah, so there's multiple mice. We chose a particular one which had about 6 to 7 data points, and then hence we had to apply the interpolation to get a smooth approximation for our ground truth data.
Okay. Have you considered using embeddings for, like, because you've got, basically, it's like you've got each mouse is going to have like a different parameter in the way, but like they all follow basically the same sigmoid-ish curve, right?
Yes.
So if you had like embeddings, then you could have that like this mice is like slope is like this much, and the next mice slope is like that much, and so on.
We haven't considered that yet, but I'd definitely love to like talk more about that and like potentially apply that.
Okay. All right.
Thank
Thank you
you.
very much.
Thanks a lot.
Hi. Just to clarify, I think the earlier question was how many different trajectories did you train the neural ODE on? It appears that it was only one. I mean, one curve did have 6 points, but the number of curves that you trained on was only one.
Yes, that's right. As of
Cool.
now, yes.
And then earlier also you mentioned that the definition of a neural ODE is based on replacing the fixed parameters of the equation, but actually what you're doing is you're replacing the right-hand side entirely, not just the parameters.
Yeah.
And later on also, you mentioned that you foresee expected improvement through the tuning of hyperparameters for the neural ODE in the sense of forecasting, which is, I guess you could call extrapolation, but it's unclear how that would bear any fruit, given that in order for you to be able to extrapolate, you have to learn something about the underlying dynamics, and just simply changing the layer size or the number of hidden nodes won't necessarily meaningfully try and address that directly. It'll be more like rolling the dice and hopefully something would do better. So I'm curious about what the actual strategy is to improve the dynamics outside of kind of twiddling knobs and hoping that there's some outcome.
So we definitely want to train our neural ODE model on multiple data sets. So as I mentioned, this was on a particular model. So having that, like sort of that generalizability would help us achieve, as you said, it will be able to learn the dynamics itself.
Cool,
And then,
thanks.
So a question over here.
Hi, thank you for the great talk. Very enthusiastic. I'm just curious about how you thought about first of all, like changing the differential equation, because you use this I forgot the name, like
the Gompertz.
yeah, model, but like a hyperbolic tangent function is a classical solution of any other differential equation. Have you thought about probably changing that instead of doing, that's my first question. And then second, you mentioned that you have a lot of different mice data set. Do they all follow a sigmoidal function?
Yes, so firstly, to address the first question, so we just chose the Gompertz ODE because it is one of the most widely used ODE models for tumor growth, but you're absolutely right. There's multiple ODE as well as PDE models that we will explore as one of the next steps. For example, there's the logistic equation, the exponential, the Burt-Allenby, and so on. So those can also definitely be utilized for training our neural ODE as well as our UDE. As far as the second question goes, so I'm sorry, could you please?
Oh yeah, like if all of them follow a sigmoidal function.
Yeah, yes. So generally, we did notice that the volumes did follow a sigmoidal growth. So yeah.
Okay, just slightly. You said that you have once you reach steady state, or I mean like the saturation point, some of them start to grow. Do you think that's a numerical artifact, or does it have a physical meaning? Like tumors, I mean, I believe tumors can grow even beyond that, right?
Yeah, potentially. So as you said, that it could be possible that our models are able to capture those intricacies and potentially are sort of implying that it's not reached the carrying capacity yet. So that could be a reason, but we're yet to explore that. So hopefully we're able to find. Yeah, absolutely.
Okay, any more questions? I think we have time for maybe one more. Okay.
Yeah, nice talk. I just have one thought and then a question. Actually, about the question that was just asked, the first one. I've worked a little bit with them before, neural ODEs, and my thought on like using a different, like you use the Gomperts. My thought was always find like a mechanistic model that sort of fits the data pretty well, and then I think the point is that then modeling those mechanistic parameters with like the neural network, like you said, introduces the flexibility, and the shortcoming of the mechanistic model is not that the model's bad, but that the parameters just aren't flexible. So I was just, that's an opinion I've held, so I'm wondering what you or maybe anybody else in the room thinks about that, for one. And then I forgot the second thing I was going to say, so I'll let you guys go.
Yeah, I mean, that's definitely quite interesting. I mean, I have only started working in the SciML space for the last couple months, but as far as I know, based on my knowledge, I feel like it's like, I guess like changing the models might help, but again, it just depends on the way it's trained. And perhaps even using better data might help.
All right. If we can be quick.
Okay. The second thing, I guess, was have you looked into modeling like interventions like at some given time point in like the middle of like the time course of neural ODE or of the tumor growth or something like that?
So just to clarify, what exactly do you mean by interventions? So as in the... Right. Yeah, yeah. So that's definitely one of the things that we did set out to explore. And as I said, this is ongoing research. So we will certainly look at the effect of radiation, for example, or various things like maybe changes in diet and so on. So yeah, that would be one of the next steps for sure. But yeah, thanks for bringing that up.
Okay, why don't you all join me to thank our speaker once more for a wonderful talk. Thank you all so much for joining the first part of the Julia Health Mini Symposium. We're breaking right now. We'll be resuming after lunch break and a keynote following by Dr. Karandeep Singh. We'll be in the same room. We'll be picking up with Dr. Oscar Laverni talking about cock survival models. So hope to see you all very soon. Thank you so much. I don't know if I was officially it, but yeah. Were you here for the presentations before the JuliaCon ones? Yes. Okay. Yeah. I was, but Bill not really helped just yet, so I wasn't sure. No, those are on like stuff. Yeah, no, geospatial diet stuff. No, so but now I'll be here for the rest of like JuliaCon makes the building, which I think is actually like the rest of the day. Yeah, schedule. I'm only here for the first talk after lunch, and then I'm okay. The day, so okay, okay, so good. I will see you there. Okay, and question with this, so I'm trying to remember because I know each room has like runners as well. Yeah, that's me. Are you a runner? Okay, okay. So I guess after that first talk, do you know if there will be another runner? Yeah. And I will give you his name or her name. Okay, okay. Saya. I don't know who Saya is. Saya will be very happy. Okay, great. Because what? Yeah, I'll have them.
those are the only two notes that
Okay.
are important to pass on.
Okay. Awesome. Great.
Well, I'll see you up front.
Yeah, thank you so much. And you said it was Trevor?
Trevor, yes.
Okay, got you.
Great to meet you.
Great to meet you too. Nice to meet you. Jacob Zelko. Nice to meet you. But okay, but I will be around though for the rest of the week though. So
We will see.
I'll see you. I'll see you. You guys grab lunch. I'll see you. I'll see you.
Don't get too stressed.
Oh, I'm not. I mean, honestly, so after today, I'm so happy because actually I had a job interview this morning.
Yeah.
Before. So I'm actually good right now.
Okay, okay.
So, all right, you guys take care. I'll see you. I'll see you.
just fixed it. Finally figured it out. As you walked in.
What was it?
Somehow I got to the screen where it says mirror or extend, and I pick extend. It comes up differently now. On the Macs.
Looks like I recently went to a rental park in California, and I can't think of the name of it. The background works.
Oh, it's Apple, so it could have been.
Yeah. That was it?
That was it. Yep. That would have found it if you didn't walk in the door.
Yeah. I have the effect. I'm gonna get a second cup of coffee. I should go talk that over.
I thought I slept for a long time. Then I looked at the clock. It was
to, so I'll introduce you and everything. I want to know, do I pronounce your last name Laverny? Laverny?
Laverny.
How do you say it?
Laverny.
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 Okay, I'm gonna try.
If you don't pronounce it as it is, it's no problem.
Okay, okay. And if I do it wrong, just say hi. Just
No, it's not an issue.
Okay, okay.
Um,
No, I just wanted to touch base, but okay.
yeah, don't bother.
Yeah, and I know that we're kind of in a funny. You kind of have a funny time slot because you'll present, and then immediately after that is the keynote by Karen D. And so what I'll probably do is like with your talk, we'll definitely cut it like maybe with like 2 minutes, 3 minutes before 2 o'clock, so that way people can migrate over and everything. So.
Yeah, no problem. I can do a bit shorter than expected.
Oh no, you're fine to go the full length. It's just they're not maybe only like 1 or 2 questions, if any. I just want to make sure people have time to get over to the keynote. But
yeah, no problem.
otherwise, I'm quite excited. I've been very curious what you've been up to for everything. Are you still working with Reem?
No, I'm not working with her anymore because she's starting a PhD. She started a PhD a year ago, right?
Wow.
September
I remember
24th.
this. Okay.
And so she moved.
She moved. Okay. Okay.
She moved. She's in Grenoble now.
Okay.
Working with a guy called Mathieu Besançon.
Yes, I've heard
Which
of
you
him.
may know because he's doing a lot of mixed integral linear programming.
Oh yes.
And so she's working on this kind of stuff.
That sort of stuff now.
Yeah.
Okay. Okay.
Yeah.
And
I don't really know if she. Well, we exchanged a bit,
yeah.
but I'm not sure that she likes it that much. I don't know. She didn't tell me.
Okay. Okay.
Yeah. I hope for her.
Yeah, I hope it's going well. But you're like Julia Serve could you could always come. No, that's, yeah.
I'm not sure she would like to come back. Okay. Où est-ce que j'ai mis mon verre d'eau?
Still 10 minutes or so before people start coming back.
Yeah. I'm going to smoke.
Okay. Okay. Yeah, actually, like believe it or not, like I do switch these around quite a lot. Actually, like little.
Oh, the plugins.
Yeah, yeah. Like I didn't actually think I would that much, but just when you're like at home or you're at your desk or something and you want to set up your desk or whatever, it's super nice just to have this. And then I've been able to use it like for presentations and stuff like that too. Like if I need to hot swap out a module or something, so it works. It's actually quite nice. Yeah. But the only thing though, I didn't get the model that has a GPU, so it only has CPU. So what I'm hoping is maybe someday in the future I'll get like an eGPU set up, because it does have a Thunderbolt connection.
Yeah.
I just don't know. I don't know how like strangled it will be. That's the only thing.
Basically, if you have Thunderbolt 3 or Thunderbolt 4,
Yeah.
eGPU is possible, but you get a dip in performance a bit compared to a standard GPU. That's what I have at home. And but if you wait a bit more, there is Thunderbolt 5 coming around,
Okay.
and on it you'll get better connections. In fact, it's not even Thunderbolt 5. It's just I don't know if it's part of the USB certification now. It's moved a bit, but there will be more bandwidth available for future GPUs.
Okay.
And I think there is one model or two that exists
Okay. Okay.
with bigger bandwidth, but not that much right now.
Okay. Yeah. So I mean, for my daily work, since I don't do a lot of GPU work, it's perfectly fine.
I have a GPU at home, but only to play.
Yeah, it's like with me, I'm not at the point. I'm almost at the point where I could start using a GPU, but not too much yet. Just like run some projects would be nice, but not. It's like a nice to have. It's not even like cool. So, but it's been promising. All right, we're just checking time, so we'll be starting in just a couple more minutes, like 3 minutes or so. I think people are just coming back from lunch too.
Not the best time slot.
No. It's like I said, it's a weird time because it's like you're kind of in between two. But I expect when you get started, people will just come in. Let's see. I was told though that we should start sharp at 1:30. So I guess just like 2 minutes we can go ahead and get started, and then I'm sure people will start filtering in.
Otherwise, if we are 4 in the room, we will have the opportunity to interact.
Yeah, yeah.
As much as you want.
It could be like a more discussion, perhaps. I think let me just do one quick check. All right. Are you gonna be good to get started? Okay. We'll just give it one more minute, and then we'll go ahead and get started. Let's see. It's a 30-minute presentation. Yeah. So it'll be 30 minutes, end off just maybe a couple minutes early, just so people can make it over to the next keynote.
I'm not sure I will do 30 minutes. I think it will be a bit shorter.
Okay. I'll be holding
if you want.
If it comes down to it. It's my job.
It's your job.
It'll be happening.
Okay, and if you don't do it, they don't pay you. That's it.
Well, I don't pay for
Oh, you don't get paid.
You will not be getting paid, but that's anyway.
Okay, I see that we're at 1:30, so I'll go ahead. Hey everyone, thank you so much for joining the next talk that we have prepared for the Julia Health Mini Symposium. Today we have our speaker Oscar here talking about Cox Model Go Burr, a journey to performance. So Oscar, I will turn it over to you to present. Thank you so much.
Thank you. Let me just start my timer. So this is a talk that basically tells the story that happened to me through last year. We wanted to exploit the power of Julia to implement some model, and we had a few issues. So I will try to explain why, and then we'll go on the how and through some of the results. So I need to talk in the mic. Yeah, maybe I can just take it, or you know what? Give me the other one. Is okay. That's better.
Yes.
So I come from statistics, right? And this is a bit of this is an implementation of known model in survival analysis. Survival analysis is a branch of stats that take care about time to event data. Those are data that you get when you study, for example, medicine with people dying. People might die at a certain age, but you might also end up the study before they die. And so there is a thing called censorship in those data that might happen and that need to be treated specifically in terms of stats. This theory is widely used in medicine, of course, but also in engineering for failure of equipments, in economics, and in a lot of fields. And the characteristic is the presence of censorship. I'm going to describe what it is later. The field exists as a theory since a while, and since computer came around, there was implementations of it, and most of the state-of-the-art code today is basically in R. And this work and what I'm doing since a few years is an attempt to port some of that knowledge into Julia. In R, there is one package that is called Survival, this one from CRAN, that is maintained by Teriterno, which is at the core of the ecosystem. And it's a 30 years old piece of code. It's maintained since then. And it's very, very important because this is the list of packages that depends on it. So the list is a bit long. And all those guys use the work from Teriterno, but none of them help him maintain it, basically. The guy is alone maintaining this piece of software that is used by everyone. There is an XKCD that basically applies here. This is the piece of software that we are talking about, right? With one man maintaining it since 30 years. And the guy is going to retirement in a few years. That's also a problem. But why? The question is now why? Why it happened like that? And in fact, it's a two-language problem. It's the fact that most of the underlying architecture and the underlying models are written in C and not in R. And those users are used to R and not C. And so they don't contribute because basically they cannot. So in Julia, there wasn't much. There was a few tentative at implementing some stuff around the time, but all of them did die. There was one 2 years ago that we asked if we could take back the package and start from it, and the guy that owns it never answered us. So we started again 2 years ago with this Julia Serve organization that now holds a few packages. So you have a few that are underlying and maybe background. In the base, there are a few standard types. There are a few standard distributions that are used in the field that are not in distributions.jl, so we picked the API and implemented some of the things that we needed with it. There is the rate tables.jl that implements mortality tables, which is an important kind of data that exists in this field. And there are a few ones that are more user-facing. So the first one is from last year about a very specific niche survival problem, which is called relative survival analysis. And the last one, which is the one that I'm going to talk today about, is called survival models.jl, and it provides tools to make regression on survival data. Okay, so let's go to the core. So a survival issue is an issue where we observe some characteristics from several independent patients. Let's say patients because we imagine that we are in the medicine field, but in other fields you might work with lights, for example, that might die at some time. And so we observe T and delta, which are the time to events, the survival time, and delta is the status indicatrix. It gives you a 1 if the person died, and a 0 if the person did not die at the time T. And in fact, those things are constructed from underlying time. So there is a true survival time O that we don't observe, and a censoring time C, and T is basically the minimum between the two, and delta is the indicatrix that T equals O. And on top of that, we have some covariates X that are given, and the goal is, of course, to characterize the distribution of T given X without taking into account the nuisance that is the censoring, the nuisance from C. So we have some kind of filtration that is going on. Across the time, we have more and more information that are coming on. The estimator and statistical procedure that we construct will have properties related to this filtration, martingalité, and stuff like that. The characterization of the distribution of T given X is done usually through what is called the hazard function. You might know that a distribution function, that a random variable can be characterized by its distribution function, by the density, by the survival function, which is 1 minus f. Those things are equivalent, but in survival analysis, we prefer to characterize things through their hazards, which are the negative log of the survival function, or the derivative of it. Why? Because the problem that we have here is a minimum. T is the minimum between O and C, and the hazard of a minimum is the sum of the hazards as soon as we have independence. And therefore, this characteristic function of the random variables are used in survival analysis to model things, because it allows to transform this minimum in the realm of random variable into a plus and faster subtraction, which is easier to deal with. So the Cox model, that is the subject today, was introduced in 1972, and it's basically a log linear model for the hazard function. And so it gives you lambda as lambda 0 of t times the exponential of beta times x, where beta is a vector of parameters to be fitted, and x is the covariates. It has one key feature, which is that the effect of covariates is multiplicative, and it does not depend on time. You see that there is a separation between the variable t and the variable x in the function. And this is what is called the proportional hazard assumption. This is an assumption that is usually false, but this model being old, being kind of the first one to be able to model those kind of things, it's still very predominant in the literature. And when some new data comes in, this is basically the first thing that a practitioner will try. So how does it work? From the lambda function, you can construct the likelihood, and then you simply minimize the likelihood to obtain the parameter. Of course, there is an issue because this likelihood here has two parameters, the beta and the lambda 0, but with a few hypotheses that are not that much a problem, the proportional hazard hypothesis, in fact. In the main paper, Cox was able to derive some partial likelihood that only cares about the beta, and this is the function that we are trying to minimize here. yeah. So to minimize the likelihood, we can minimize the log. So if we take the log of this function, we get something that looks like that, where the delta i's here are 0 or 1s. Here you get something that is linear in the beta, and here you get some log sum exp. So log sum exp, there is a numerical warning to be taken here. It's that the log sum exp operation is known to be unstable. And in fact, there is a way to stabilize it, which is to take the maximum out and to remove the maximum from the inputs. Because here, if the AJ are large, the sum will be not very precise, and you'll get imprecisions. But here, the AJ minus the maximum, all of them will be negative, and so this exponential will be small, and this will be much more stable. In Julia there is a package called logx function that does those kind of stuff for you if you want. Okay, so we have a loss to be minimized. So let's go. The first thing that we tried to do is basically one line of code is to take out optimization.jl and to write the loss. So here it's an NL, meaning the negative log likelihood that we are trying to minimize, because usually you want to maximize the likelihood. So if you take the negative version, you can minimize it. And it writes very easily in Julia. It's completely similar to the equation that is here, which is very nice. And in 2 lines, I have a struct here that will simply fit the model and store the beta as it should. This thing will use automatic differentiation to compute the gradient of the problem and try to solve it. I don't know what is the default. I think the default is probably LBFGS. I don't even check, but it works correctly. The issue is that it's pretty slow. It's in fact very slow because this function here is not very optimized. You see, I did it on purpose, but there is 2 times the x time beta here, which is a matrix vector product. So we are doing it twice. This is not very good. And here there is a matrix I of indicators that is very structured. And this structure can be exploited to do much better in terms of performance. So this is what we tried in the first version, is to implement the derivative by hand instead of having them computed by the automatic differentiation method. And in fact, it's not very hard to do. So you can get out the gradient, you can get out the Hessian. And if you take a second to look at it, you'll see that in the gradient here, you have a piece here that is simply the weighted mean of the x's by these w's. And here you have the weighted mean by the w's of the square of the x's minus the square of the means. So this is kind of a variance where this is kind of an expectation. For the moment, this interpretation has no interest. Well, it still has one. The main interest is that this is positive. And since it's the variance, it means that the Hessian is definitely positive, and thus the problem is strictly convex, which is a characteristic that we need to exploit if we want to achieve performance. So that was my version 1. Just implement the derivative by hand, give them to optimization.jl, and try to do better. Then I have a version 2, which is exactly the same, but where we tried to remove the type instability that we had. There wasn't that much, but mostly the allocations. And this comes from the fact that implementing the derivative by hand is not an easy task. So we had a lot of allocations in them. And the strategy is simply to pre-allocate those things and then fill them in place to be able to get the performance. And this is something that you might do for other codes too, and there are very good references online on how to do it. You need profiling tools, so there is the @prof view. You need to check allocation with alloc-check.jl, type stability, etc. So once this is done, and once we are sure that the code is as performant as it could be, you can't do much more. And the version 3 that I have, the next idea that we had was to simply get rid of the optimization.jl and implement ourselves the solving loop. In particular, to have the opportunity to pick very carefully the stopping conditions to be certain that we stop when we want, instead of using some default that we don't control. So this version 3 is basically getting back most of the problem for ourselves instead of trusting optimizations.jl. In fact, while we do that, we can also exploit the convexity at its maximum by using pure Newton-Raphson instead of some Newton with an approximated Hessian. So this was also part of the gain that we had here. So we thought that we were at the maximum, but then something else happens. It's that if you look at the Hessian here, I told you earlier that it has a variance structure, and in this variance, you can think of it as the variance of a certain random variable, where the atoms of the random variable are known. This is a data set, but the weights depend on the parameter. And in fact, you can bound this by saying that on a known support, the variance of a random variable has a maximum. This is basically the random variable that has weight 1/2 on each side of the support and 0 in the middle. And this is the variance that it has. And so we can maximize the variance and, in fact, bound the Hessian. And this gives us a convex envelope on top of our loss that we can exploit, because this bound can be computed before the gradient descent. And thus, in the middle of the hot loop, we don't have to compute the Hessian anymore. We can simply use the bound. So we have the guarantee because it's a convex envelope, and therefore it will converge. But the drawback is that the direction that will be taken by the gradient descent is a bit less optimal, of course, because it's not pure Newton-Raphson. And therefore, this will increase a bit the number of steps that the algorithm will take. And so there is a trade-off between the fact that the steps will be faster, but we will take more steps. And this trade-off has a lot of things to do with the size, the shape of the problem, which is something that we don't control that much. Okay, so there was other versions too, but that's enough. Let's go for the results. What do those implementations give? So first, the interface that we have, we tried to basically copy the interface that is available in R, and we have a simple fit function with a fit of Cox. You put a formula in here, and then the data set, and it outputs the results on this form with the name of the predictors, the betas that were fitted, their standard error, some p-value for the test that you should include or not the variable in the fit. And with that, we hope to be able to grab some of the users, because the interface will look like what they are what they are used to. And our different version can be accessed by telling it which version you want. But if you just say Cox, it will pick the best. So this is a simple test to check convergence. All of the versions were calibrated to have the same convergence criterions. So they basically converge to the same point. And the point of convergence, the loss is decreasing with the number of observations, which is normal. And here you have the runtime, finally, of the different versions. So I don't know if you can see the colors that well, but the two on top are the version 1 and version 2. The most dumb one, this is the version 0, the optimization.jl. So our tries to do better than optimization.jl were in fact not that successful. And then you have the version 4 here in green. And on the way bottom is the version 3, which is our most performant. And the red and the black line here are what R does, the red line. And the black line is what survival.jl, the previous version that existed in Julia, does. And in fact, so the red line is the R line that I was talking about at the beginning of the slides, the one that is optimized since 30 years. And we beat it completely by a factor 10 approximately. So this is very good results. Here you have only the lower ones, the most performing ones, and you see that the shape is basically the same between the two. This is because we use the same algorithm, but our implementation is better. And here you have the same shape too. One important thing to see on these graphs is that the runtime is basically linear in the number of observations here and in the number of dimensions here, which is expected from the structure of the algorithm itself, and which is nice to be verifiable. So to conclude, the fact is that with a few lines of code, we were able in a month and a half to beat the gold standard by a 10x, which is a very good result. The gold standard is in C, so we are not competing with our code, we are competing with C code. And we checked that the algorithm that they have is in fact the same that we used at the end, the theoretical algorithm, but our implementation is just plain better. Yeah, this provides also efficient and easy to use implementation of Cox in Julia that were not there before, so it's a step in the right direction. But in the package, in survival models.jl, there is also a lot of other stuff. There are non-parametric models such as Kaplan-Meier, the log-rank test, etc. And there are also parametric versions of the general hazard model, which are other models that you can use. But of course, the field is wide, and there are a lot of other stuff that should be implemented around those models. In particular, the possibility to add non-linearity in the regression through splines or something like that will be very useful to the practitioners that we managed to discuss with. All right, thank you very much. If you have a few questions.
Awesome. Thank you so much for the wonderful talk, Oscar. At this point, floor is open for questions. So if anyone has any questions, feel free to ask. And if you can speak into the microphone, just so.
Sure. Yeah. So yeah, one is time-varying covariates. Is that in your to-do? Is that like splines and nonlinearities? Is time-varying covariates in there?
Yeah, this could be. Yeah.
And then second question, maybe harder question. Can you replace the underlying C code for R, so R users can use this Julia implementation? What would that look like if you thought
I would
through?
love to do that, but I think you have to talk to other people for that, to discuss with the -- trim. There is a talk this afternoon, I think, and the goal is that when Julia will be able to compile into a DLL, .so library that is thin enough, and then we can take this .so, put it into an R package, and ship it on CRAN without them even knowing, which will be much easier than what we are doing for the moment, which is shipping a full Julia into the R package, which is not possible, and so it forces users from R to install it aside. They don't even have the right version all the time, so it's a bit more finicky. But I don't think it's ready right now. Maybe in a year or two. Yeah. But yeah, that will be a huge step forward.
Another question?
Hi, thank you. You seem to have very impressive results, especially compared to the current standards. I mean, you say 10x. Do you have any examples of like applications where this time improvement would be especially helpful, especially since this is like a health mini symposium in that operation?
Yeah. I have a colleague at my lab that is using the underlying optimization routine to do it in each leaf of a running random forest. And therefore, the number of times that she has to compute this minimum is very, very large. And using the one from R, she gets runtimes of about a week. And we are trying to use that now, but it's not done yet. But we hope to get improvements, right?
Would you expect 10 times improvement? Or?
Yeah, definitely, because the rest of the code is just moving stuff around. So.
Thank you.
Okay, I think we got time for about 2 or 3 more questions. Any more questions?
Do you have your eyes on any other models that you want to make go burr?
Yeah. If we just go to Survival models.jl. I don't even find it. Should be here. There is this thing called general hazard that basically has a hazard structure that is like that, which means the notation here uses h's instead of lambdas, but it's almost the same. There is still the same factor here, but there is another one here, basically. And the beta should not be the same. This is another category of model that basically encompasses a lot of applications. And for the moment, the version that we have is not very fast. So we have a lot of documentation and runtime and tests, so everything is all right, but the performance is not very good. So we are working on it.
What's the difference in terms of what's the practical difference between the accelerated failure time model and the Cox model, just like intuitively?
It's just a different specification of the model equations, right? And in fact, there are others. I don't see them. I see here. There are other way to specify this kind of hazard equations, and we are trying to do something comprehensive to encompass all of them at once. So the generality is there already, but the performance not yet. And with some of them and some of the way to parameterize it, they have interpretations that are not the same. And for the doctors, it's important to be able to get the interpretation that they want out of the parameters that come out of the model.
All right, I'm actually going to ask a question myself real quick. Kind of similar to some questions earlier, tremendous results, especially compared to the state of the art, compared to, I guess, the last 40 years or so. I'm very curious, so far in your journey with JuliaServe and the work that you've been doing here, how has it been received in these venues where they are still using, say, like Survival, the R package, or these other ecosystems? How has been engaging that part of the, I guess, community around survival analysis? How has that looked to you so far?
Yeah, it's a good question. It's been hard because if you don't give them enough, they won't move. Basically, the answer that I have is this is great, what you just did. Do you also have the opportunity to do that, and that? No, not yet. I have to implement it. But those guys that are using those models have the tendency to be spoiled because they live in a world where everyone recodes the same thing, so it's very inefficient. But the library is huge, right? And basically, they need a lot of it. So, yeah, that's the answer that I can give you right now. It's that we need to do more before some of them will try to switch.
Okay. Thank you. I was wondering about that because within the Julia Health ecosystem, that's also been something we struggle with. We think a lot about how to bring these sort of users into the ecosystem where it's like we do have these performance benefits, but there's such a plethora of other tools in history, like going back 40 years as opposed to maybe 4 years for Julia Health. That's a tricky problem. I was just curious.
Yeah, and at the beginning we tried. The first time that I tried the thing, we did go for netsurvival.jl, which is implementing some niche of survival analysis, with the hope that the people into that niche will be able to move easier than others. And actually that worked a bit more. We attacked a very specific point, and this worked, and we had people move. But here we are trying to give them the general environment that they need, and so it's harder, right? There are more stuff to do.
That makes sense. Well, everyone, thank you again so much for presenting Oscar. If we can give Oscar another round of applause, thank you so much for answering the questions and presenting. I'll just do a quick little logistics announcement. The keynote speech by Karandeep Singh is happening right across the hall. We'll be resuming the Julia Health Mini Symposium after the keynote in this same room. So if you're interested, we'll be hearing about Calm MRI, State of Julia Health, and some other activities across Julia Health. Thank you so much for joining, and we'll see you all in a little bit. vectors. I think that's the one you need. Okay.
Is it fine if I test it?
Yep.
Okay.
It's kind of a weird little working schedule because it was from lunch. Tom, academia. Which I guess.
Late from lunch.
Yeah, and it's a tough time. It's kind of a tough time. But no, I gotta talk to Oscar more. I want to figure out how can I support. There's so much stuff I want to do, man. Just because like that talk was I thought incredible, especially with him saying like, hey, we outclassed 40 years of performance tweaks just using Julia. He's like, the problem now is just start competing with raw C. Which is pretty impressive.
We still have cases and examples where we beat it quite substantially.
I know.
Because of the difficulty of optimizing raw C. Yes.
Shooting yourself in the foot or something. Yeah. And he was
Shooting
just
yourself into a corner, shooting yourself in the foot, just so many different ways that your system can start to go really
bad, really bad.
You want to optimize it more, but you just can't. Technical debt or whatever it's called. Other times, there's just one key optimization.
Yeah.
A small piece of code.
Promise, I straight up thought I might just be exhausted, but I was staring at your wallpaper and I'm like, it's moving.
It is kind of moving because of the projector.
Okay.
Okay. But it seems to be working. Thank you.
Awesome.
Yeah, you never know, right?
You never know. Are you running like Linux distribution? Okay.
Yes,
Yeah.
an alpha version of one.
Exactly. You just never know, man. These guys does.
Written in Rust, yeah.
Written in living on the edge. I love it. All right. I'll join you over there in just a minute. I'll see you over by join you too. So just making sure I'm smooth. What did you say? Yeah. I need to talk to I know. I'm definitely going to. Trinity, I wish I could talk to him, but he was telling me that he's actually in
your session here, right? Are you in your session? Okay.
Yeah. On the like after the keynote, we're doing the Julia Health Mini Symposium. The Julia Health Mini Symposium.
For MRI.
Yeah. So it'll be after the keynote talk, and Carlos will be giving that talk.
Oh, okay.
So
I volunteer to work in this room.
yeah, yeah. So we'll be here, but if you come back in like 40 minutes, that's when the talk starts.
Oh, okay. So you going here the keynotes.
Yeah, yeah.
What's your name?
Oh, I'm
sorry.
so sorry. I'm Jacob Zelko. Nice to meet you.
Nice to meet you too.
Thank you. should probably, I would like love to pick your brain about it. I'd be curious your opinions, because
I know we're that deep into the cloud system.
yeah,
I'm more of a
I guess you'd be
very
more in the
thorough
clinical,
machines,
yeah, like a radiology side part, which is part of the operations. But yeah, it was just like, it's really interesting. I mean, it's very hard though, and it's like, since I work on the high level sorts of things like health economics, health systems, it's hard for me to look at statistics like that and not think about problems of like equity, work representation, stuff like that. So
still really cool.
But I think he briefly touched into that.
He did.
He was saying like he would obscure some details to the LLM, so
Yeah.
he didn't do like predictions based on that.
Based on that, which is like, that's a tricky one. I used to work with non-profit based in New York City, and what we were doing was like some of the early stuff with using LLMs for like the note-taking stuff he was talking about, the note casting, which is interesting. Again, though, as you know, like dependent on what the clinician and the attending records, you know, so it's always, it's tricky. It's tricky. Oh, by the way, you fully converted me to Porto. I use it for everything.
It's so good.
It is so good.
Oh, it's I tried writing my presentation in Porto and failed.
Oh, really?
So I went back to Google Docs.
Critical fit.
I was like, alright, everyone's using Porto, I'll try this thing out. I must have done something wrong.
Yeah, when you get some version working, and then it's awesome.
Yes, yeah.
Also, it was a little bit finicky with the Julia engine, but now I think
Oh,
has
now
been
it's just
fixed.
fine. Now
Yeah.
it's rock solid. I have no problem with it.
I was trying to show that.
Sounds like a skill issue.
Yeah, this new like quarter notebook runner.
Yeah.
It's super great.
Is good.
There's a talk on it now.
Yep.
I think so. Yeah.
Julius is gonna do that, or keep that or something. It's all good.
It is a whole blur. Alright, so we'll get started just in like 2 minutes here, and then
Yeah. Yeah.
I'm assuming people will trickle in too. So.
Yeah. Some people are still in the plenary room.
Oh yeah, no doubt.
I can unfortunately only stay for one talk because then I have to go to talks about clients too.
You're skipping my state of Julia health talk.
Wait,
How
when is
dare
that?
you.
When is that?
It's right after his talk.
It's 1 hour. Like if you're gonna stay until 4, like.
No, we're just messing with them.
Yeah, there's so much cool
Just
cool
stuff
stuff going on
happening.
like at the same time.
Yeah,
I always watch like the videos of that.
There are at least 3 people whose talks I want to go to, which were co-located with my talks.
Oh,
Like,
yeah. Well, me and, so I didn't get a chance to talk to them, but me and Gabriel,
Okay.
do you know Gabriel?
Yeah.
Yeah.
Well, I don't know him, but I think I
his
know.
name,
Yeah.
like we were chatting.
Gabriel Barral?
No, different one.
Oh.
Neurobox, Gabriel.
Ah.
Yeah.
Oh no, then I don't know.
No, but he and I were talking because at the same time our health mini symposium was running is the Neuro mini symposium. which
Oh
is
my
like-
god.
So we were trying to figure out why that was, and we weren't able to get the things adjusted in time. 'cause
That's
I had already-
unfortunate.
Yeah, because Gabriel was like, I want to be here to listen to your talks. And I'm like, I want to listen to your talks. So, but okay, let's see. We got about 1 minute, and then we can go ahead and decide. I'm assuming people will probably trickle in as like as they're kind of getting the tea and everything. So.
There were so many talks.
Yeah.
I guess I want to as well. But like this one.
All right, Mike, should we be good? Mike, should we be good to go? Oh, Mike. Hey, Mike. Mike. Oh. Hey, Mike.
Is he okay?
Hey, Mike. Mike. Mike.
Is he okay? Like,
Breathing.
is he breathing?
He is breathing.
Okay. That's an interesting one.
Does it work already? Just, maybe you should check.
Mike?
I don't know.
Oh, wait, I think I heard you on the mic.
Hello, hello? Yeah, the audio I think is working, but I'm not sure if it's live streaming. Yeah. I can check.
I'm also worried about my
Live stream. It'll be on the live stream if it is.
Yeah, I'm checking the live stream.
Okay.
Well, maybe it's ready.
Well, he's not waking up, which I'm a little concerned about.
I think it says it will be back soon, so...
So it's not live yet. Okay.
Yeah.
Maybe you can ask him from this.
Yeah, hang on.
You know, I wait.
Technical difficulty. I will be right back. If you want to keep talking to him, I'll be right back.
Is he okay? Like, I'm not even sure if he's sleeping or had a heart attack.
No, he's breathing. He's definitely breathing.
Yeah. Okay. He has very deep sleep, or?
I don't know to release it. Okay. He loves to sleep.
Oh my God. Well, it gives us a little bit more time for people to come. That's hilarious.
That's a good product there.
Yes? That's actually a simulation.
So is he still asleep currently?
Yeah, which is weird.
As far as we know.
Yes.
So this is our. He's not waking up.
Well, we tried.
That could be like a problem, like.
Does he?
Oh. Oh, I'm glad you woke up. Oh my God. Oh, we were worried. Okay.
No, you're okay.
Are you all right?
You're okay though?
Yeah.
Okay.
We just didn't have a good night's sleep last night. We're about to start.
Yeah, we're yeah. Okay, okay.
Yeah.
I'm glad he woke up.
So, all right.
Good?
We're ready. You get ready?
We're good.
Okay, okay.
Okay.
All right, awesome. Thank you everyone so much for rejoining the Julia Health Mini Symposium. Today we are joined by Dr. Carlos Castillo-Pasi talking about the state of coma MRI. Carlos, I will turn it over to you to talk about what's new with coma MRI.
Thank you very much for the introduction. Just in case you want to see the presentation on your phone or computer, I will put the link here for a few seconds. If not, you will see it now. Okay, so why simulate MRI? I assume people here are not MRI experts, so it could be not completely apparent why would this be useful at all. So MRI has a few challenges. The MRI physics are complex and solutions often are not intuitive, so simulations are very useful for teaching MRI physics. Also, MRI scans are costly in time and money, so that makes the feedback loop of full sequence design very slow. And simulation can improve on it by simulating first and then go to the scanner. And also, sharing MRI data is complicated. there's ethics problems, patient privacy issues, and no large data set is available. For example, the fast MRI, that is the biggest one, has around 9,000 images, but ImageNet has like 14 million. So it's not really comparable, the amount of data we have for medical imaging to something that could be useful for deep learning or stuff like that. And other fields are doing, or similar fields are doing simulations, but because the cost of trial and error is very high, so they just play in this digital playground and they can answer some questions they are interested in. In our case is how we can get the faster and more useful image. So just to show you less abstractly what this means, for example, low field MRI has become popular now because it's less expensive, so it's more affordable, and it would be like more useful for more people. But the problem is that if you try to do cardiac scans in these low field scans without doing optimization, the quality is not very good. But you can use simulations to improve the sequence parameters and get a beautiful image like this. Moreover, you can show that at the top row, you have this low field image, and at the bottom row, you have this conventional field image, and they have very similar image quality, and these are patients. You can also get information about quantitative information that you can extract by simulating signal dictionaries. For example, here I'm showing T1 and T2 maps that you can obtain dynamically for hearts. And what are we exactly simulating? We're simulating the block equations, which is this differential equation that you can see here. And basically, what we are interested in measuring is this M, that is the magnetization, that is our measurement. And we can change B, that is our magnetic field or pulse sequence. These other parameters, M0, T1, and T2, are tissue properties that depend on basically the person, not the scanner. So this is not special, it's just a differential equation, so it has a right-hand side, and we know how to solve those, but for MRI, we need to solve millions or hundreds of them. So for example, for 2D, if we have an image that is 100 by 100, suddenly we have 10,000 spins or 10,000 of these differential equations. But if you have 3D high-resolution images, we can have 100 million spins. So the computational costs start like going up quite rapidly. How are we simulating this? We are using the operator splitting method to be more efficient about it and simulate faster. That basically what it does is that it separates the differential equation in two additive terms, solves each one separately, and then combines the solutions. And this has very nice convergent properties and is good enough for most cases, actually. ComMRI implement this in a user-friendly way, and all of the things I have talked to, for example, the sequence is defined by a sequence file, the tissue parameters are defined by a phantom file, and this gets simulated by ComMRI, and you get an output that is the raw data. For example, if you take a photo and you get the raw data, that's something we obtained before processing it and getting the final image. So we use Julia because it has very similar syntax to MATLAB, which is very commonly used for the MRI community. It has multi-threading, GPU support, and GUI support. So we implemented this in a easy-to-use user interface that you can select, for example, your sequence of interest, press simulate, and then you get your results or reconstructed image. And you can export all of this to a .mat because I know that people want to use MATLAB still, so we have made it easier by exporting it this way. One of the cool things about this problem is that all of the differential equations that I just mentioned are totally independent. So you can do each one in each thread of a GPU. And the other thing that is kind of important is that ComMRI implemented PulseSeq, that is an open source definition for this sequence or how you take the image. So you have a text file that is something like this that describes each block of the sequence, and it gets parsed to something like this that describes how the magnetic fields are changing in time. And this is what's being simulated. And moreover, all of these plots are interactive, so you can zoom in and if you want more detail about one area of the sequence. So in our first paper, we basically showed that the accuracy was comparable to like sundials. That is a conventional differential equation solver that is used by Gembris, an MRI simulator. And the accuracy is very good, and the simulation speed is like 100 or 200 times faster. Here we have more comparisons with other simulators, but basically the main point is that just by using Julia GPU array programming, we were able to be faster than existing simulators. So what's new? One of the first things we quickly realized is that it's not scalable to have a package that has everything. So we separated stuff. First, ComMRI is the one that has only the UI definition. ComMRI base defines the structs. There are these arrows that are passed as files with ComMRI files. And ComMRI core is the one that is actually doing the simulation. We added this also in ComMRI plots to be able to visualize these data structures. One of the cool things that we managed to separate the CIs for all of this and also the code coverages. So by using tags in code coverage, you can separate them and you can have statistics in a monorepo for all of these packages. Another thing that one Google Summer of Code student did is that he implemented kernel abstractions because we were using array-based programming, so we wanted to try kernel-based programming. And just by using package extensions, what you can do is that you can simulate in the CPU just by using this code. But when you import CUDA, suddenly the ComMRI core CUDA extension is loaded and everything is running the GPU, the same NVIDIA GPU, and the same with AMD, Apple Silicon, and Intel. And he achieved huge performance wins because he also optimized these GPU kernels. These CIs are also separate, so we can separate between JuliaCon and the LTS and all of these backends by using BuildKite. Julia kindly offered, and we can use Julia's computers to run this because I don't have an Apple and Intel and stuff like that. So this runs automatically in each commit or pull request. And we also do benchmarks, so we can check if there's some performance regression. As I said, we optimize the simulations by using kernel programming and basically completely optimize the speed and memory allocations of the simulator. And you can see there that by using GPU array programming, that was our first implementation, you don't necessarily get faster simulation speeds compared to CPU, like optimized CPU code, multi-threaded CPU code. But just by programming with this GPU kernel programming with kernel abstractions, you can get around 50 or 100 times faster, depending if you compare it to array-based or CPU-based simulations. Another thing that is good to note is that array-based programming, when you start getting the number of spins very high up, goes out of memory. So you are not even able to do, for example, simulations with 10 to the 8 spins. But you can do it because of the optimizations with kernel-based programming. We also included distributed computing, so we can run the simulations of a brain, for example, separating it in different parts. Each one we can send to different GPUs by using distributed.jl. You get a signal that is for each one of these parts of the phantom. And the cool thing is that you can just add them together, and that's exactly the solution of doing it all at once. So this is how it looks in Julia. You basically define everywhere something similar to what I just showed you, but in the end, you just add all of the signals together for each device. And you can also send this to like a cluster by using Slurm. Pablo Villacorta from the University of Valladolid also implemented motion models, so you can simulate more scenarios regarding cardiac MRI. For example, here, he's simulating an aorta that has some flow, and you can see the corresponding signal and image. So these motions are composable. We kind of got inspired by some Julia packages about animations, so you can combine them together. So you can have translational motion that has a time range from 0 to 1, and you have another translational motion that starts from 1 to 2, and then you can combine them together. And you can see here this interactive plot of the brain basically moving right and up. So the first second goes right, and then the second one goes up. So you can combine them together. And we also have the rotations and more stuff like that, but this is just the simplest. Moreover, you can define arbitrary paths of all of these particles or spins. And this is useful for simulating more complicated phenomena like diffusion. And here, for example, you can see that the spins start all at the same position, but you can see how they start diffusing when I advance through time. So you can do quite complicated stuff. And going back to the aorta, you can simulate flow motion. So for example, here we have a coarctation that is basically a reduction of the diameter of the aorta that generates some like jet-like velocity distributions. And we simulated this with 5 million spins and using an NVIDIA GPU. And we compared ourselves to the state of the art, that is CMR sim. And we can see that we're around like 4 times faster just because we are using kernels and Julia, which made it so much easier to program all of this. This comparison is not strictly correct because we need to do some post-processing before doing this simulation to generate the particle trajectories. But after that, as that's only done once, we can just run this in 9 minutes. We can also do simulations with, for example, 7 million spins or more, and distribute this in multiple GPUs. And you can see here how the execution time scales with the number of GPUs. So we can also do distributed simulations of these like complex flows and motions. And you can do more stuff. Here I just showed a few examples, but there's more cardiac relevant things that you can do. And I just put a few examples here. So what's next? I didn't mention it, but when you generally do an MRI scan, what they put on top of you is a coil. And as you can see, it has like multiple elements. So the idea of that is to accelerate the speed of the acquisition. So each element will basically hear the signal coming from different parts of the body. So you have to reconstruct like smaller images for each one, and then you can combine them together. And we basically have this implemented in a pull request already. So you can see here like how the different coils measure signal from different parts of the brain, and then you can combine them together to get the brain at the final image. We have also delved in enzyme automatic differentiation. So we haven't been able to differentiate comma yet because some problems with Julia 1.11 and enzyme. But we were able to differentiate some CPU version of the code, like toy project. And we can get an RF envelope that we can simulate. And then at the bottom, you can see the actual acquisition that we did that matches the simulation. Obviously, there's a long way to go, so the RF looks a little bit weird. So if you see at the left, that's what it should look like, or approximately. So we still need to like toy with this to make it better. So conclusions. CommMRI has been growing a lot in the last 2 years. My previous talk at 2023, CommMRI had around 40 stars, but now it has 155, which is great. And here I put a map of a few places where I know they have used it. And obviously there has been a lot of collaborators, and this wouldn't be possible without them. Also, a slight propaganda. I want to show you, if you liked CommMRI, you can give it a star. And also, please join the Julian Health Slack channel, because if you are interested in health and Julia, you should definitely be there. A few acknowledgements to my professors at Chile, Pablo Irarrázaval, René Bodnar, Claudia Prieto, and also a few people from Julia, like Jacob Selko, Dylan, Tim Bizard, and other people that have worked on this, and also my group at Stanford. And thank you very much.
Thank you so much for the wonderful talk, Carlos. At this point, the floor is open to any questions for Carlos. So if anyone has any questions, feel free to ask. No? Yeah.
Okay, thank you. My name is Isaiah. So I want to ask about the Kuma MRI, the simulation part.
Yeah.
does it simulation the functionality of the MRI, or it only simulates the imaging part?
It simulates what the magnetization would do to the magnetic field. So basically, it simulates from doing the sequence to acquiring the actual data. That's what it's trying to get, the raw data that you acquire when you do an MRI acquisition.
Oh, so if I get it right, it also simulates the magnetic field as well.
Yeah, it simulates how the magnetic field changes, and you can vary that with the sequence object and basically modify it as you like and see the results.
All right, thank you.
Hi, I'm from the Martino Center.
Oh.
So we do a lot of fMRI and MRS. I just wanted to make you aware, we have a technology known as Brain Dancer, which provides a ground truth brain activity to which you can compare the measured signal. So it provides a way to separate out thermal from multiplicative noise, which becomes important if you're modeling the MR signal, because there's scanner-specific noise that changes every time you do a scan. So I just wanted to make you aware of this technology in case it was useful to you. So Jonathan Palomani, who just moved to Stanford, he was one of the developers with us.
Oh, really?
And Larry Walt, actually.
Okay, I will definitely take a look into this. For right now, what we're doing is just simulating without considering any noise. Obviously, noise, how to simulate noise is complicated, especially if you have multiple coils. So I would be interested in looking into this. Thank you. How's it called again? Brain Dancer?
Yeah, it's called Brain Dancer because the problem is that the scanner is changing every time. And so if you use a static phantom, you can optimize over stability, but you would never want to do that for fMRI because then you'd be eliminating your signal as well. And so what Brain Dancer does is it actually produces a ground truth signal. So you can compare the measured and actual signal, learn the noise characteristics for each scan, and then subtract them out. So from a modeling standpoint, it's very helpful because it means that your data is going to be just much cleaner once you take out the scanner-specific changes that occur from scan to scan.
Yeah, that's definitely a interesting thing to explore. Like we have recently, we acquired recently a new scanner, so we want to characterize it and basically be able to simulate more realistically. And one part is, I'm not sure if this is only for noise because of the mechanical vibrations, but we want to characterize the gradients, fluctuations. So we have a way to measure it, and I'll be interested in looking into this.
Okay, we do have time for additional questions. Any more? Oh.
Yeah, so I did have one just out of curiosity.
Yeah.
You mentioned that you did monorepo CI.
Yeah.
And you also mentioned that you split the tests. So you split I'm assuming you split the tests per subpackage.
Yes.
So do you get code curve numbers from the individual subpackages? Because for example, if you run tests on coma MRI, that would also exercise functions in all the subpackages. So do those get added together?
Yeah, what we're doing is that the code coverage has one thing that is called flags. So what you can do is that you run the test for example, coma MRI base and pass the code coverage to the flag base. And then you can generate a batch for each of these flags. So that's how you can get subpackage specific code coverage.
I see. So I guess what I was asking was, does the code that is covered in the tests of coma MRI.jl make its way to the code coverage statistic in coma MRI base.jl?
Yes.
Oh, it does. Oh, okay.
Yes.
Oh, okay. I see. Okay, very cool. Very cool.
Yeah. So basically, like any relevant package that could touch one of these, you just add a flag, and that gets included to the code coverage flag.
Okay, very cool.
Yeah. Yeah, not a lot of people are using it, but it's kind of useful actually.
I have a bunch of monorepo, so.
Okay.
Especially for GPU stuff, you can also we were talking about flags, and you can run the code coverage of the GPU part in build kite and send it to the flag of MRI core, and gets added to the overall code coverage of that package.
I think I'll actually jump in with a question real quick, Carlos.
Yep.
So just kind of like looking future forward with kind of the results that you're talking about with comparison to state of the art, how you're like really kind of outpacing a lot of this, like some of the state of the art currently right now. I'm just curious, in terms of like future work, do you see, like, since this is so tethered into the Julia ecosystem, I'm just kind of curious, do you see like any potential roadblocks or barriers that are, you know, prohibiting you from pursuing certain aspects that you'd be interested in exploring? Or is it more a matter of, you know, manpower, time, implementing the work? I'm just kind of curious if you're limited by implementation or where there might be a bottleneck.
Yeah, right now we really want to do like automatic differentiation stuff, but it's just not very well documented, and so it's kind of like hacky. You need to like ask in the Julia Slack. So that is slowing down the progress a little bit, but maybe I can manage to talk to a few people here and make it work.
Yeah. Okay, any more questions for Carlos? Okay, I think that is it for questions. So Carlos, thank you so much for your time, and thank you everyone for attending. All right, we'll have a few minutes just before we get started on the next topic. Oh yeah, it was perfect. It worked out. I don't know who though off the top of my head. Okay. Hmm?
Oh no, just gonna say hi. Sean Wu told me to say hi to you.
Oh yes, we need to connect. I'll grab. Definitely will. We need to chat.
I want to hear.
Okay, we'll get started here in just a few minutes, and we'll be talking about the state of Julia Health. Okay, we are at time, so we can go ahead and get started. So hello everyone, thank you so much for being able to come to today's talk. So this is a general state of Julia Health, high-level overview, summary of what has been going on in Julia Health over, I guess I'd say not only the last year, but also the last couple of years, since this is our first ever Julia Health Mini Symposium. So a huge welcome to everyone here who's able to make it. It was, been fantastic so far. Just a few notes on some logistics, though. Just due to various constraints, you'll see on the schedule that some of our members who are presenting were not able to make it here due to various reasons, such as visa problems, so on and so forth. So there will be work still being presented. You'll just see me up here presenting on their behalf a little later today. But with that said, thank you so much for joining. I am Jacob Zelko. I am the current leader of the Julia Health organization, started around 2021, 2022. Just to give a brief background about myself is that my undergraduate studies was in biomedical engineering, finished up studies recently in applied mathematics. In the past, I held roles at Georgia Tech Research Institute and the United States Centers for Disease Control. Most recently, I was a RU Institute affiliate dedicated to looking at bringing cutting-edge healthcare research along the New England corridor. And these days, I actually work as a research affiliate with the Center for Computational Epidemiology, Public Health Informatics Lab at University of Saskatchewan. Kind of moving on from there. You might also know me from various other sorts of work within Google Summer of Code and also the Algebraic Julia ecosystem and community. We'll skip that for now. Just a fun little slide showing what I get up to. But we want to talk about Julia Health. So to give a quick overview on the general history, since this is our first ever mini symposium, and for some of you this might be the first time you're hearing about Julia Health, is that this was more or less founded in 2020 by Dr. Dylan Maluthgay while he was actually still a clinical MD PhD student at Brown University. And this was created specifically at the time to coordinate some discussions around responses to the COVID-19 pandemic. As of today, I don't know why we have 2 copies there, but we have about approximately 300 members of the Julia Health organization worldwide. This can range from researchers such as clinical field or computational specialists and informaticians, as well as beginners or just enthusiasts who are students, maybe hobbyists, or other folks interested in seeing how we can kind of combine Julia for health research. Just to give a quick synopsis and history of some of our major events since I've taken leadership. Back in summer of 2024, we hosted our first ever Julia Health workshop. We called it the Warsaw Workshop. This was hosted in Warsaw, Poland, with the National Information Processing Institute in partnership with Dr. Jacob Matura, who sadly could not be here today, but you'll hear about his work a little later. And then also today, we have the first ever Julia Health mini symposium here at JuliaCon. So to give a quick synopsis overview of the ecosystem, we'll dive more into this in just a moment. Julia Health serves as kind of just a centralizing focal point for folks who are interested in using Julia for a variety of different healthcare research questions, as well as health problems that are interested in researching using Julia. It's home to dozens of Julia packages. There's multiple different sub-ecosystems, such as the medical imaging sub-ecosystem, observational health ecosystem, and many more other emerging ecosystems that have organically evolved over time as interest has allowed. Additionally, there's now Julia Health blog, which we'll talk about as a huge success for the community so far, and also multiple Google Summer of Code Fellows, which we'll especially recognize in a little bit. And this to talk briefly about our community presence. I mentioned we have about 300 people worldwide. Here is where we are. So we're generally speaking located on the various parts of the internet, such as the Julia Slack and the Health and Medicine channel, on the Julia Zulip being the Biology, Health, and Medicine channel, and also YouTube. Thanks to Viral Shah and some of the other Julia creators and maintainers, they've given us permission to actually post the occasional Julia Health YouTube video directly to the Julia Health Julia language platform on YouTube to about 100,000 people worldwide. Additionally, we do have monthly meetings. These are generally focused right now these days for time zones specific to Americas, Africa, and Europe. There has been some attempts at also generating a Asia-Oceania specific chapter. I'll talk a bit more about those details in a little bit. And then there's also a huge presence with Julia Health with our relationship with Google Summer of Code. Now, to kind of coalesce some of the community goals that have emerged over the past couple of years is that, these are kind of the 4 main goals that we have as a community right now. We're still kind of hashing these out formally, but with the last Julia Health year in review meeting that we have at the end of every year. We decided that these 4 were kind of the most central to us as a community so far, which is that Julia Health serves as a place for providing a place for discussing and exploring innovation and health research across the Julia ecosystem. Health equity should be and is a priority, foundational priority for the Julia Health ecosystem. It is not an afterthought, but something that is core and fundamental to us. Julia Health should enable the development of new research software and workflows for practical use cases. And additionally, share approaches in these techniques through monthly meetings, discussions, and blog posts. So to give a kind of highlight of some of the quote, like best hits so far of what's been happening both within the ecosystem, the package development, and also research outputs, the next couple of slides will be talking around what have we been able to achieve collectively. So the first package, which you just recently heard about, is Coma MRI. Just want to highlight this package. For those who have not heard about it, Coma MRI is a Julia package meant to simulate general MRI scenarios. Seen here is the awesome kind of graphical user interface that Coma MRI provides. And to give a high-level overview of what Coma MRI, some of the features where it takes place, is that spearheaded by Dr. Carlos Castillo-Passi and his team over at Stanford University. These features, which come directly from the Coma MRI documentation, which is extremely well done. I highly recommend anyone to look at who is interested in documentation to look at Coma MRI as a great example of package documentation. Is that this allows things such as fast simulations by using CPU, GPU parallelization, compatibility with community standards, interactive visualizations, cross-platform support, and a very friendly user interface for people with no programming skills. Just some quick statistics. Is that globally becoming very popular with over 1,500 downloads, rising in popularity, at least on GitHub, if GitHub stars or any metric, just to report that. And there's a variety of different use cases that this could be used for. And additionally, just a huge congratulations to the Coma MRI team, as they have recently actually been able to publish a paper on Coma MRI specifically, I think it was this year. So huge congratulations to their team. The next package I want to highlight is neuroanalyzer.jl. Neuroanalyzer.jl is a Julia toolbox for analyzing neurophysiological data. This is spearheaded by Adam Wazinski, based out of the Medical University of Lodz. For the Neuroanalyzer toolbox, this features and focuses more on analysis, where you can import and edit neurophysiological data, visualize EEG, MEP, EDA signals, submodules for simulation and studies, scriptable and parallelizable analysis pipelines. So, again, some quick statistics, quick potential use cases, and similarly, congratulations to Dr. Wazinski, as he has also published a paper on Neuroanalyzer just also this year with the Journal of Open Source Software. So huge congratulations to that team. And then kind of the final high-level package that I want to highlight is Thunderbolt.jl. Thunderbolt.jl is a modular shared memory high-performance framework for multi-scale cardiac multiphysics. This is spearheaded by Dennis out of Ruhr University, Bochum. It features cardiac mechanics, cardiac electrophysiology, simulation, and model development, and high-performance parallel solvers. This work is still rapidly ongoing, as Dennis has informed me, but it's definitely a package to look out for in the Julia Health ecosystem, and extremely exciting to see just the variety of different tools that we have for simulation across a variety of different domains and use cases that we're interested in. I'm going to skip this for time right now. I might come back to talking about HealthBase a little later, but I'll skip this for now. I want to move on to community highlights. And as I mentioned kind of earlier, there's been some big developments within the Julia Health ecosystem. To start with, on some of the softer ones, is that we actually have a wonderful new Julia Health blog, which comes as courtesy of Div Goyal and Hitarth Shah. So a huge thank you to these community contributors in the ecosystem for that. And to show you just really quickly what that looks like, shown here is kind of the landing page right now we have, not only for the blog, but also for the website. It gives a quick and easy sort of entry point to some of the package and ecosystems, but not only in Julia Health, but also around Julia Health. As shown here, we have multiple different sort of friend and partner organizations that we think are very much related to the work that we want to be doing. And we always want to use our platform to increase discoverability of not only these packages, but also these communities, so people know exactly where they can go to keep doing their work productively in Julia. And then moving into the blog itself, you actually have a variety of different blog posts being published over the last year or so that the Julia Health blog has been around. So a huge thank you to not only just contributors in the community, but also Google Summer of Code fellows and participants in Julia Health. And we'll talk about Google Summer of Code in a little bit here. But that is currently the Julia Health blog, and there's lots of hope and aspiration around that. Moving on to Google Summer of Code, I did want to take a moment to really shout out and recognize all of our community participants so far for Google Summer of Code. As I mentioned, Julia Health has been around since about 2020. I've been leader here since 2021, 2022, and we didn't actually start Google Summer of Code until 2023. I accidentally just noticed I missed the date. Ryan Kurolf is 24, but I actually first ever Google Summer of Code participant was Farida Abdulaziz, and she kind of kicked off the Google Summer of Code revolution that has taken place within the Julia Health ecosystem. We've had a variety of different contributors and partners from all parts of the globe contributing to different packages and ecosystems within Julia Health. And none of this would not be, a lot of these features and packages and ecosystem development you'd see now would not be as nearly as exciting if it wasn't for them. So a huge thank you to all of our Google Summer of Code contributors. I'll just list them off really quickly. Farida, Ryan, Jay, Jan, Div, Michaela, and Indu. So thank you all so much for your participation so far. And then to also kind of hit some highlights on research. So as I mentioned, there's a variety of different ecosystems that are emerging within Julia Health. For the ecosystems right now, I'm just kind of cherry picking some different papers that have been published. So here are 3 papers that were kind of published in the last year or two. So this is showing not only that Julia Health is growing in terms of packages, having tools that are becoming useful, but also showing like how these packages and tools are translating into direct research outcomes, or at least enabling future research endeavors. So huge congratulations to Castillo Pasti's group, Wazinski's group, and many more people here. It's great to say that there's too many papers for me to put on one slide right now, which I'm really excited to report about. Observational health, there's been some work being done with fairness and health equity and disparities with disease definitions of disease. Within kind of an other general category, just to kind of poke or focus on some right now, we have a publication that was in collaboration with the Julia Dynamics community, which is looking at biomedical signal processing for physiological signal analysis in open science using the Julia language and associated software. And then we have some other sorts of conference events as well as forthcoming papers around using some of these Julia Health and public health related ideas for various domains of applied mathematics. So there's a lot of stuff happening right now within the research output part of the Julia Health ecosystem, and I'm excited to see it continue growing. As I said, this is a quick snapshot, and something that we'd love to do in the future is maybe to syndicate or better track where the publications are coming from and from who within the Julia Health ecosystem. And so that brings me to kind of part 6, which is where we want to grow. And there's kind of 2 parts here to this part that I want to talk about, where after months of communication about Julia Health as a community growing over the couple of years here or so, is that we've identified some parts where it seems like Julia Health is actually succeeding as a community. And of course, that also goes without saying that we want to continue this pattern of success for these particular domains or topics. And the good news is that folks both new and kind of who have been around in the ecosystem do say that the Julia Health ecosystem is a welcoming, inclusive, and supportive community and environment and ecosystem, which is definitely a goal that we want to enable and achieve for anyone who might be interested in broader health research exploration and developments. There's also been a tremendous success with also highlighting and sharing the work in community settings. This has actually led to very practical, actual collaborations happening within the Julia Health ecosystem between various members of the Julia Health community. So as a result, there have been some events, packages, publications being built jointly in between this sort of confluence of sharing information. We continue to look at engaging with the broader ecosystem, building community relationships with like Julia Bio, or BioJulia, I always forget which way. I'm pretty sure it's BioJulia and some other adjacent sort of related communities. and continuing to recognize contributions just as a whole within Julia Health itself. That has been something that I think we've succeeded on, and it seems like the community has converged to say that we have. Now, the community as a whole has also been saying parts where Julia can grow. And I think the number one most important, vital part of Julia Health as a whole ecosystem is the problem of documentation. Right now, there's been common feedback saying that Julia Health as a whole for packages that we have often can lack a unified feeling between documentation. You might have some folks using Documenter Press. You might have Documenter being used, or you might even just have README files, or perhaps even just doc strings in your code. So it's very hard to sometimes find an entry point into packages or tools that are being used within the ecosystem. There needs to be maybe more templates that people can more easily follow, not only for package development, but also to say, here's the workflow on how you might want to use the packages with not only Julia Health packages, but also other packages across the broader Julia ecosystem. And additionally, kind of related to that is this notion of making this all more comprehensible, because it's very easy for an expert to say, you just use the package like that, compose it with this other package, and you're off to the races. But for a newcomer who's not familiar both with Julia and the broader Julia landscape, figuring out these ways of composition that just solve your problem without having to create a new massive monolithic package aren't oftentimes obvious. And so there's kind of a problem here where Julia Health can grow more. And additionally, there's also the notion of enabling more attendees. So as I mentioned earlier, we kind of said a foundation is to provide an equitable environment that is inclusive and open to all. And something that is a barrier has been time zones. Time zones is kind of the bane of, I think, all of our existences in one way or another. So there has been some community effort to look at how we can make community meetings happen both at times that work, over in Eastern and Western hemispheres. So far, those efforts are still undergoing, where we're trying new things out, but the effort is being made, but obviously we can still focus there and continue to grow. So this kind of brings me to future and community goals, where there's kind of different potential different directions we could potentially be going, such as building across the ecosystem. What can we think about and do here? So for example, something small, low-hanging fruits are things like NUM-focused small development grants that can be used for open source, open science communities and research ecosystems to help ameliorate some of these problems that we've identified as a community as a whole, and explore perhaps other partnerships with other organizations or other Julia GitHub organizations, or even more formally in other venues, to see how we can actually build this ecosystem, make it more accessible to all, and also improve kind of just overall ergonomics of how it means to work with this ecosystem. Additionally, there is also some work being done to explore other fields. As you'll hear a little later today, there's work looking at how we could potentially implement things like large language models into some of these health sub-ecosystems, things like geospatial health informatics, and also there is the kind of massive sort of unspoken recognition that still to this day, Julia is great, we love Julia, but right now kind of where the state of the art when it comes to social sciences, public health research is still the R programming language. And there has been work being done with groups like XKDR within Julia to actually address things like survey methodology and survey design, and working with that sort of data and eventually harmonizing it across other data assets and sources within a Julia environment. So I'll kind of end off here. I decided to kind of end the talk just a little early because I thought, this is kind of going to attract some maybe new folks here, as well as to leave us some time to talk about, as a community, maybe where do we want to grow potentially, or where would you like to see Julia Health grow? Even if you're not a member of the community, all feedback is valuable here. So I'll go ahead and end off here, and I open the floor to discussions. So thank you so much.
Thank you so much for your intro. I wish I had known about this. Unfortunately, in terms of the planning of this conference, right across the hall, there is actually also a session on neuroblocks. Neuroblocks is a computational neuroscience platform that is really designed for healthcare applications, both in terms of being able to model neurological and psychiatric disorders mechanistically to behaviorally, and also their therapeutic interventions. So I just wanted to make you aware this is a Julia package, and we definitely welcome collaborators and users.
No, absolutely. Thank you so much for mentioning that, because I also noticed that tragically, kind of last minute, that somehow we had this co-parallel track going on. Because I agree with you. I think there's just definitely synergies that all the ecosystems and community can explore here. So thank you for making me aware. I'll definitely follow up. I know. Yeah. Any more thoughts or questions from folks?
May I ask, oh God, what are some core capabilities that you think might be good for the goals that you have, like maybe data about health across the world, or like what kinds of things do you think are missing and would be useful to a beginning audience thinking about equitability in health?
Yeah, it's an excellent question. I would say actually my first thought actually isn't so much just diving into particularly we need to build a new package per se, as I found I think the R ecosystem really succeeds in bringing data to the users really easily. You have tools like our data sets or tidy data, I think is another one. Just basically a lot of these packages are kind of pre-built, ready to go, that allow you to just load in sample data sets to get you exploring. And something that ends up happening within the Julia Health ecosystem is still it's not quite fully, I'd say, at capacity to actually bring people data to explore these questions of, be it equity or just other health research domains in general. So something that's a really low-hanging fruit is not only questions around how could we build, perhaps better unified data APIs, or just some general health sample data type of package that allows people to bring this into their ecosystem or bring this into their own workflow to follow through tutorials. There's been some work done to actually create a package that provides and provisions some sample data sources to work with. But at this point, it's mostly just a matter of someone taking that on and making it their project. So that would be my first kind of answer. But then as it comes to health equity and those considerations in general, something that I think is really powerful, I need myself personally, and I'm sure the ecosystem can too, is, I look at the ecosystem like MLJ, the Julia MLJ ecosystem, and they have a variety of tools there for class imbalance and sort of these other sorts of analyses that you could work with, analyzing where there might be class imbalance structures within your data sets itself. And something that, a cross-pollination effort that should probably take place is saying okay, we have, here's the MLJ pipeline, and now here's how you can, leverage the Julia Health, maybe data provisioning tools or some of these Julia Health tools to load in your data. And then here's how to think about equity as you go forward. So again, it's a matter of kind of just having to do it, but also the wherewithal to know how things compose. So it's a tricky problem. It's because it's not just a technical problem, it's also a very social problem.
Yeah, mine is a contribution. It's where do you want to go? It's about the documentation. I want to see a big improvement on the documentations. Especially it allows to attract the new entry-level people.
No, yeah, I guess we'd say specifically for the Julia Health ecosystem, something that we're looking into right now is we actually do have a written proposal for here's what we would do, revamp across the Julia Health ecosystem to provide a better entry point in terms of documentation of how people can get involved. Something, I skipped it earlier, but I can show it now because this is, I think, goes well with the discussion, is that there is a package that we're slowly working on called healthbase.jl. Healthbase.jl its goal is to be an extremely lightweight package that provides a unified sort of API and interface, as well as provide helper functions that are in support of a variety of different workflows that someone might want to be doing within Julia Health. And so what I'm imagining is at some point we can have a variety of different, say, workflow guides where, for example, if you want to do an observational health study, here's exactly how to do it using the Julia Health tools. And also, for example, here I'm saying using data frames. So I'm also showing not only how to use Julia Health tools to accomplish goals that you're interested in, but also how it composes with the rest of the ecosystem. Because what we found is that sometimes the solution in Julia isn't to create another package. It's just to create another composition and document that composition.
Any questions?
All right. Well, hey, I guess I'll come back. Alrighty. Thank you all so much for your time. We'll have a few minutes before the next talk starts, and then we will be hearing the next talk. So thank you all so much for being able to join today. Appreciate you.
It's unfortunate that the neuroscience symposium was happening at the same time.
Yeah, yeah. Okay, so are you Anish? Yeah. Okay, great. Okay. Then I'll let you. So let me go ahead and grab you everything. So there is the cable. Then if you do you need HDMI or which one do you need?
I don't know.
Oh.
Will HTML work here?
It should. We can try it.
Yeah.
All right. When you're ready, when you have your computer open, we can
Yeah.
plug it in and try it out. All right. I'll let you. Okay. But yeah, yeah, I agree with those. Well, let's look at next week.
So now it's the dream talks.
What did you say?
Now it's the dream. Dash dream talk.
Oh yeah. Is that happening right now too?
Yeah.
Okay.
Sorry, just a second.
So, Nish, I will be sitting right like there. I'll just hold up signs just to say like 5 minutes or 1 minute.
Okay.
Yeah,
Thank you.
of course. Yeah, a few more minutes before we get started.
Yeah.
Me too.
So you work there from Sean.
Conference talk.
Oh, that's
So
a
far.
conference.
That was a conference
Andrew.
talk.
That's
Andrew.
Yeah,
Okay.
yeah, yeah.
We need to talk
Call me
more.
Drew. Yeah, call me Drew.
Drew. Okay. Because like, yeah, the venerable Sean Lawrence Wu was saying, I need to talk to you. So I'm here.
I love Sean.
I know, and he was just saying not only that I need to talk to you, but I need symmetric words category theory. And somehow he was saying that Drew would understand this.
I do.
And,
Of course.
and
That's
so
very
that's
I'm
what
not
Sean
very good at
said.
it, but like I get it. I get it.
So
He keeps yeah, he's great. He keeps putting category theory in the middle of everything I ever do.
where he finds a way, he'll just slip it in.
Speaking of undocumented, hatchets is the most undocumented thing I've seen in my life.
We should talk about that. I want to talk to you about this.
All right,
I'll be
later.
right back. I'm just gonna grab some water before we get started. We'll be starting in just 1 minute. You all good on your side? Okay. All right. I'll go ahead and introduce you.
Yeah, sure.
All right. Thank you, everyone, so much for joining today. And today we are joined by Anish Sarkar, who is presenting on his work today. I will turn it over to Anish to take it from here. Thank you so much.
I would first like to thank the JuliaCon organizers for giving me the chance to present my work here. I've stumbled upon Julia on my final year of graduation when I tried to harness the power of machine learning to learn complex natural phenomenon. And one interesting project I've picked up on is trying to accurately model the tumor volume or the tumor volume trajectory over time, while also taking into consideration the complex immunoreaction mechanism. The challenge remains that the standard mathematical model like Gomper's model cannot fully capture the real-life complex scenarios. So what I have tried is I've tried to augment the ODE by using two more neural networks that are correction neural network and immune response neural network. What this do is the immune response network takes the normalized volume and the normalized immune cell level or the immune fraction, and it outputs a immune mediated suppression rate. The final output layer is constrained to output values between 0 to 1 as a sigmoid activation function is applied on it, and the time and the correction neural network takes into account the normalized volume and the normalized time so that it can model the capture the residuals that the Gomper's model failed to capture, like when the tumor is in early growth phase or is late growth phase or is saturating, then the unmodeled complex dynamics that oftentimes Gomper's model fail to accurately predict, our time-aware correction neural network tried to predict that. And the final output layer is also constrained in this case. The values are between -1 to 1, -1 to 1 as 10H activation layer is applied to it. I would like to briefly talk about the data set. The primary data set has 5 columns. The first 2 columns have the categorical identifier of the clinical trial or the observation trials that were performed or were recorded. And I've tried to use all the informations in the data set to model this tumor volume trajectory over time. And all of these things were done by Julia's pretty convenient packages, like Flux for initializing the neural networks, differential equations for solving the ODE, Zygote for automatic differentiation, etc. These packages help me to not to be boggled down by complex codes and write the codes in a simple, intuitive manner that everyone can interpret or understand. And also constrained my model so that the growth rate and the carrying capacity remains in a biologically plausible range. And there is also a penalty when our model predicts negative volume. As you can see from the these graphs that our model achieved a pretty good performance. It's R2 square score having 0.997, and it also successfully modeled the immune mediated suppression that resulted in an average of 30.25% volume reduction. The standard Gompers model achieved an R2 score of 0.85 to 0.92, and whereas my model achieved an R2 score of 0.997, although there are some caveats that our data set is limited. There are only 11 trials, but I tried to generalize the model as much as I could by splitting the dataset into training and testing. And although I tried to generalize the model, but there is still risk of overfitting, so it needs some more larger trial. Next, you can see that our immune neural network learned a complex non-linear response, same as the time-aware correction network. And the time-aware correction network was designed in such a way that it took into account the volume also while correcting the growth rate. So our final ODE equation was Gomper's growth minus the immune network's output plus the correction network's output. We also found some pretty interesting biological phenomenon, that there is a negative correlation between the tumor growth rate and the immune response with R, with the value of R is R equals to minus 0.82. Also, as you can see from the right side graph, that when the tumor growth rate peaks, then the immune response starts to go up, and as the immune response starts to go up, the tumor growth shrinks down, and the tumor growth plateaus, and the immune response saturates. We will also try to analyze our model, that we tried to classify the tumor groups into 4 classes that are complete response, partial response, stable disease, and progressive disease. But unfortunately, my dataset had no tumor trajectory that shrank down the time. But as you can see that from the graph, that there are the stable growth tumor groups. There were 5 of them, and the progressive disease were 6 of them. That means that the 5 of them, the 5 of the tumor group were actually responded to the immune mediated suppression as the tumor growth rate saturates. And what I am trying to work on right now is replacing the scientific parameters of Gomper's model, that is the growth rate and the carrying capacity, with neural networks so that our model remains mechanistic, yet it is flexible and data driven. And also there are potential to integrate into the Julia Health system while trying to leverage the genetic information that are available in bio.jl package. And that is it. And thank you. And I would like to.
Awesome.
I am happy to answer any questions you might have.
Thank you. We unfortunately won't have time for questions, but again, thank you so much for presenting, and we'll go ahead and get the next speaker set up in just a moment. Okay, great. We are all set to get started. Give me just one moment here to start the timer. Okay. Thank you so much for everyone joining today. This is the talk, Mapping Patient Treatment Pathways in Population Health. A special note about this talk today is this is actually the work of Sanjay Lange, who is unfortunately unable to make it here today, so I'm presenting on his behalf as also his Google Summer of Code mentor for the 2024 to 2025 year. So this is the work of Jay. Quick note about Jay, just since he's not able to be here, he is a first-year bachelor's degree student in IIT Hyderabad, majoring in computer sciences and engineering, native of Maharashtra, and his research interests include high-performance computing, concurrency controls, and computational biomedicine. So a little bit of background about what is treatment pathways and what this notion is that a patient pathway tracks a sequence of treatments patients undergo beyond just drug usage statistics. These are things like a sort of event-based model or way of thinking around a patient's continuum of care as they interact with the health system, such as receiving diagnoses, prescriptions, so on and so forth. They help us analyze treatment patterns and adherence to clinical guidelines and drug distribution over time for not only singular individual patients, but also huge populations of patients. Oftentimes, patient pathways research is rooted in real-world data, such as electronic health records, patient medical claims, and disease registries. But again, there still is limitations around interoperability and resource needs. But as of today, this discussion usually happens in the context of observational health research. So to give a quick picture or diagram of what a treatment pathway can look like and how complicated it can be, this comes from the paper Treatment Patterns in Our Package to Facilitate the Standardized Development and Analysis of Treatment Patterns Across Disease Domains by Dr. Aniek Marcus. So shown on the diagram, I'm not going to really emphasize every single part of the diagram, but rather just know on the left-hand side, we can define a variety of different eras and events taking place over time. There could be an era that might be event A, an era that's event B, and an event C. And actually, the particular part of this diagram that I want to draw your attention to is this final one on the bottom where you can kind of see there's an event A, a stacked group of A plus B plus C, and also individual C in event A. The reason why you might want to do that in a treatment pathway is as a patient can incur certain conditions or prescriptions or so on and so forth, is that many of these events may be overlapping in the terms of their continuum of care, and you will want to collapse that into a single time frame or time interval. So these pathways can get extremely complicated just looking at this diagram. And so our goal for this project was to really look at, in general terms here, is to look at life pre-diagnosis, diagnosis, the initial treatment a patient receives, and what it looks like living with the condition after they receive that condition. So we're really interested in that entire continuum from first encounter with the health system to whenever they leave the health system or whatever condition that we're interested in, we stop monitoring that. So how that looked is during Google Summer of Code, the coding period last year, we ended up prototyping and developing the package omopcdmpathways.jl. This took direct inspiration from that particular R treatment patterns package, but actually sought to generalize it much further beyond just looking at conditions, but also incorporating things such as health economics, health systems, and treating encounters with not only a health system, but where it took place, such as an inpatient, outpatient care setting, or what sort of visit is occurring. We can have that flexibility within OMOP-CDM patient pathways. So our methodology here was in particular, I mentioned earlier that we were using these electronic health records and patient medical claims. We actually use this thing called the OMOP Common Data Model. I'll have a blown up picture of it on the top right. But the OMOP Common Data Model is a database schema that encapsulates and records the relations that exist between patient data coming from hospital systems, and it houses electronic health records and much more. Globally, the reason why I include that map in the bottom right is to say that this is actually quite a ubiquitous data model and is used by nearly 1 billion patients globally across different countries. In fact, a fun fact is that South Korea, for example, actually has standardized much of their medical health systems infrastructure on this particular database model. So it drives research in a variety of different domains, and there's a lot of reason to want to understand this. And patient pathways, or understanding patient pathways through the OMOP-CDM data model, is a very very easy low piece of hanging fruit that we can easily incorporate on and develop further technologies for. This is the actual OMOP-CDM database schema. Each of these white blocks here represents tables in our database schema where patient data is digested and processed and stored. And actually, this is it blown up entirely, where you can see not only are the tables kind of obfuscated at this point. I wanted to emphasize this to show that now each of these squares not only includes the tables, they also include all the features for the tables. So this is actually an extremely complicated schema that tries its best to capture all these dynamics that we'd be interested in knowing about in a patient's care trajectory. So as of right now, with the Google Summer of Code package, we've been able to look at things like error duration, such as how long someone's been experiencing an event, what discrete events are taking place, how they overlap over a single time series per each patient, and also look at how we can collapse, kind of as I mentioned earlier, multiple events into one single event, such that we can get that sort of consolidated timeline that we saw previously in this kind of bottom part here that's a little bit busy, but it's emphasizing, again, just the complexity of how we might want to understand and coalesce different events together. And so some future work here is that we want to continue implementing this package. Right now, we're very close to actually having a full means of extracting patient pathways per patient on an individual basis. And then we want to create individual visualizations like sunburst plots, and also look at how we can maybe treat these sort of signals or this time series in terms of a digital signal processing approach, or other sorts of rolling average filters that we could apply to these pathways that are recorded on a population level scale. So thank you very much. And again, I just want to emphasize, Jay was the one unable to make it today, and he's the one responsible for the lion's share of this work here. So a huge thank you to Jay. So at this time, we'll take any questions. I think we have time for maybe one question, if there's one. All right. If there's no questions, we can move on to the next talk. Which will be me again. which I'll be standing up here. So give me just a second to load that up. A second. Okay. Give me just a second here, everyone. All right, I guess we can go ahead and get started. So this is, again, another piece of joint work. This is a collaboration, actually, between myself and Dr. Jacob Matura, based out of Lublin, Poland. Like I was mentioning earlier, Jacob is unable to be here, so I'll be presenting on his behalf, where we're talking about cardio-oncology, a data-driven approach to risk prediction. Just making sure everything looks good. Great. So this project that we've been working on over the past year or so involves kind of this background that in this landscape of cancer research, as well as the intersection of cancer research with cardiovascular health, is that these are two massive leading causes of mortality globally, and cancer survivors on average face a 2 to 6-fold times higher risk of cardiovascular events due to a variety of different risk factors as one receives cancer care and treatment. And so what we have been looking at right now is thinking around, as someone who receives or encounters a myocardial infarction event, a heart attack, and then goes on to subsequently receive cancer care, our question is how well we can develop and validate an explainable algorithm to predict another myocardial infarction event taking place after this cancer treatment and diagnosis. So some of our objectives and key goals here has been looking at identifying the most significant clinical predictors of recurrent myocardial infarction, creating a transparent, reproducible pipeline for this entire sort of analysis being done in the Julia ecosystem and Julia Health ecosystem, and working with Jacob Matura's team of clinical experts alongside of kind of the more computational side of things here, because as a whole, this collaboration encompasses working with Dr. Jacob Matura, who's not only a technologist, but also a medical trained physician, and his group of individuals who are also medical trained physicians or attending physicians over in the National Information Processing Institute over in Poland. And then also here in the United States side is myself and Professor Justin Mandrides, who is a mathematician and statistician at Northeastern University. So between these collaborations, we've been kind of threading the needle to figure out what makes most sense from a clinical side, a mathematical side, and implementation side. So to speak of our approach, is that as we've been working with observational health data, actually very similar to the data that we were just talking about with patient medical claims and electronic health records, is this question of data heterogeneity. Because once we start exploring these different sort of populations, we very quickly see how patient populations can change and evolve over time, as well as just in general when we look at a nationwide scale. The reason for this in particular is that we're working with a 35 million patient database that comes from Northeastern University to actually explore and recognize what sort of patient cancer populations that we have across the United States represented by this data. And here, we're actually using a bit of a hybrid approach, because while we are using tools from the Julia Health ecosystem, we're also using other tools from the Odyssey ecosystem, which is the Observational Health Data Sciences and Informatics Consortium. It's a bit of a mouthful, so they go by Odyssey. And to actually talk about how we're doing that is, let me pull up an example of an Odyssey tool called Atlas. So Atlas provides a one-stop shop for both technologists and clinicians to actually allow you, and I'll zoom in just a little bit, to allow you to define very comprehensively a definition of disease for a population that you most care about or are interested in. So in this particular study, we actually have gone through and defined over 40 different populations based off of conditions, prescriptions, and diagnoses individuals have received over the course of their care in this data set that we're working with. So to give you an example, so this is an example for kidney cancer. We're looking for any condition of, in this case, kidney cancer. So shown here just very quickly is like some various types of kidney cancer diseases or definitions that are diagnosed. And we also include what are known as descendants of these concepts. This is a whole nother discussion, but oftentimes in clinical ontology, you have these kind of high-level definitions of disease, but then you have multiple different subtypes of these definitions of disease, and very specific ones related back to a particular disorder that you're interested in. And so as a result, you can end up defining your definition of disease and report this definition of disease in either plain text, shown here, JSON, or SQL. And this is using the Odyssey tool, Atlas, to do all of this. Now, you might be wondering, okay, that's great. We have this tool. Now, how do we actually bring it into Julia and actually start doing our analysis? So for that, I'll switch over to a very small, brief demo here. So give me just a second. So what we can do is we can go ahead and say using HealthBase. And this is a package within the Julia Health ecosystem that provides a lot of convenience functions. We can load in drwatson.jl. And so you can see that the extension for HealthBase, or the extension for Dr. Watson in HealthBase, has been loaded. We can go ahead and initialize a study. So I'll say initialize study, and we'll call it demo study. We'll go ahead and put in my username for GitHub. And so I'll just take a second. So it's using Dr. Watson under the hood to kind of provide a really nice, easy-to-use interface to actually create very quickly a skeleton for a study that we want to run. So now we have this full study defined. We'll go ahead and add a development package that will be released very soon called Odyssey API that allows us to actually pull down the sort of clinical information that we want from Atlas. So we'll go ahead and say using Odyssey API. And now what we can do is we can say, let's download the definition for kidney cancer. So right now, this is the value for kidney cancer as per Atlas. That's how it's stored. So I can say download cohort definition, throw in that ID. And then there's a convenience function in HealthBase called cohorts directory if you're working with an observational study. And what this will do is it will go ahead and send an HTTP request under the hood using an API built around Odyssey API and Atlas itself, and gives us actually that JSON representation of the cohorts that we'd be interested in. And so if we want to, we can jump over here, go into our cohorts directory, and look very quickly to see, like, behold, at the top, third line, it says kidney cancer, and we can automatically automate all of our workflows from the GUI setting, working with clinical partners, and bring it right into Julia to work with this. Now, what I'll pause kind of here is to say that at this juncture, you might say, like, we have our definition. How do I parse this? Well, there would be additional tools such as, and I'll give you an example of this from healthbase.jl's documentation. There are additional tools such as Odyssey cohort expressions that after you've downloaded your definition of disease, you can go ahead and translate this particular JSON representation into FunSQL, which is a domain-specific language written in Julia to parse out SQL expressions. But in this case, we use it to actually translate that JSON representation of a cohort into SQL itself. And then we can actually execute this cohort definition or this patient population definition against a patient database. And this is just an example to show, like, how it could be done. So switching back to the rest of our presentation here, that's been kind of our process where we've been taking HealthBase to create a single Julia-based processing ecosystem. We use SQL under the hood, kind of under the guise of this Atlas tool. And we collaboratively work together both with clinical partners and computational scientists to define what is the definition of disease that we're most curious about. And finally, we move to, I'll kind of skip ahead just for sake of time. We skip to our modeling strategy, which is using things like machine learning in Julia's ecosystem, or the MLJ package, to look at things like XGBoost and some other tree-based models, as well as probabilistic graphical models coming from Genie, which is a separate software from Genie.jl. But we're using that as well as part of our pipeline here once we have defined our 43 different cohort definitions to then take the data forward and see how we can actually define and work with this prediction problem. To kind of wrap up to say where we're at with the current status is that our process, our pipeline has been successful. We're able to work with these data definitions. The biggest hindrance right now is still making sure that these clinical definitions are fully matching and mapping to exactly what the clinicians are looking for, expecting to see with each population that we generate. this is not a problem of the actual tools being wrong, but rather just how we're defining our disease as both a clinician and computational science team. But it's a great power and capability that Julia Health provides, as well as some of these other tools to actually work with collaboratively in a same shared environment to achieve a common goal, in this case, doing cancer prediction. And so in short, that is where we're at. Here's our references for this presentation. And again, huge thank you to Jacob Matura and Justin Mangiarides for supporting this work. Okay, I think there's time for maybe one question, if anyone has any questions. Okay, then we'll move to our final talk, which is also going to be me floating up here. Hang on just a second. Okay, so this will be our final talk for the Julia Health Mini Symposium today. And this is, we'll go ahead and get started in just a second. All right, so we'll go ahead and get started. So thank you everyone who is able to make it, who was able to join. This is the RAG LLM workflow for observational health research using Julia Health LLM. Again, this is work done by Param Thakkar. He was unable to make it as well, but again, I wanted to emphasize and share the work that he's been really pursuing in bringing the Julia Health ecosystem to the world of large language model design and utilization. This is Param. He is based in Mumbai, India, and this work that we're talking about is mostly driven by him, so a huge thank you to his work. With that being said, let's go ahead and dive into the background and the rest of this talk. So what is the background here? Well, the background, just to give a quick overview, large language models, we all know, or at least are aware of them. And as we know that large language models are AI systems trained on vast amounts of text data to understand, generate, and reason with human language. They're built on top of transformer architecture and has multiple different key features. But I think the most applicable or understandable feature that we know about is things like chatbots like ChatGPT, DALL-E, and a couple other code generation tools like Claude Code, for example. There can be multiple different problems with these LLM-based approaches, which we'll talk about, such as hallucination or generating biased sort of content. And just an example, here's kind of your garden variety of different sorts of large language models being used in the world right now. So moving on from there, so as you all know, so Julia Health kind of has this goal of being an open source community and initiative focused on applying the Julia programming language to advance medicine, healthcare, and biomedical research. It brings together developers, researchers, clinicians to build high-performance, scalable, composable tools to accelerate innovation in the health and life sciences. So you might wonder, why combine Julia Health with LLMs, this sort of technology that can be very biased, that can be very inaccurate, and potentially lead to potential harms? So let's talk a little bit about that and what we tried to achieve here with our project. So the idea is that in Julia Health, and a lot of constrained workflows that we can talk about, is sometimes they can be very manual, time-consuming workflows within exploratory data analysis, be it writing handwritten SQL queries, or other sorts of technical sort of explorations that require a lot of domain expertise if you want to do a small proof of concept. Large language models, as we know, can generate complex queries from plain English, could help in the sense of building patient groups without coding in a Julia Health setting, and use feedback to adjust queries and definitions within a Julia Health workflow, especially built around observational health or other sorts of research endeavors. The idea here is that this could be faster, more scalable, accessible to non-experts, while also preserving and being conscientious of potential biases that can arise in this sort of ecosystem process. So to give an example, this is what some parts of the world have done. So this is a product out of the Observational Health Data Sciences and Informatics Consortium called the Query Library. And if you see here, there are a variety of different queries that have been handwritten over time. This is mostly a query library that I think has been built over a decade that encode very painstakingly queries people have written to address certain problems that they're interested in, such as conditions stratified by age, group, age, race, and gender, things like that, so on and so forth. And the idea here is to potentially use this sort of large language model generation tool to train upon these sort of queries that have been written over time, and to target things like data models that use observational health data, like claims or electronic health records, in particular to enable reproducible sort of data analysis pipelines using RAG-based architecture. And the idea also is that this could lay the foundation for scalable AI tools in general for Julia Health and provide kind of the first pass or the first entry point for the potential that LLMs could have in a Julia Health workflow or environment. So to talk briefly about the methodology is that in the methodology, there's a variety of different tools that we're using here, as well as data sources. For example, within the different knowledge sources that we're using the Book of Odyssey, which contains guides to methods and tools for observational health research, the FunSQL documentation, which provides documentation for a Julia library used in medical data querying, amongst other sort of data visualization, data analysis tooling, and the OMOP CDM schema description, which provides a standard structure for organizing health data. So taking all this different sort of knowledge information, we've actually built a RAG-based or PG vector-based, I should rephrase that. We built a vector-based database using PG vector that chunks up and indexes all this different sort of information coming from these different sources using the Julia package simpleindexer.jl and also drwatson.jl to maintain and work with our study that we're doing here. So Prom has been really ambitious and really productive with determining how large language models can be used in Julia Health, such as actually developing a training corpus on Hugging Face itself. So if you want to use the data, we'll show a link to this in just a moment. But here we've been able to actually build our own data set of FunSQL queries based on real-world clinical query examples, using things like the query library as a reference, which is available under open source licensing. We're using different data sources, and now we're actually in the process right now of standing up and setting up our own configuration testing harness to validate these sort of generated SQL queries that are coming off of the Julia Health LLM, and investigating how they actually work in real time against an actual synthetic patient database. So shown here, kind of a little blurry, my apologies, is our first ever kind of like FunSQL Hugging Face library that we have on Hugging Face. So Julia Health actually now has a Hugging Face presence. So if you are using Hugging Face and want to be hosting data sources or other tools here, please let me know. Happy to get you hooked up with this. As we do qualify as an open source org, we do get a couple different benefits. But this is just our first kind of pass at creating a data set where we have, for example, a concept, we have a query, we have the plain text description, the SQL query that is being written, and then also not shown is the FunSQL translation to be used as a training data set. So to speak about what other tools we're using within the Julia ecosystem is some core Julia Gen AI tools such as prompting tools, RAG tools that come directly from Julia Gen AI. And then to speak to data embedding and storage, we use File Chunker. The particular model that we've been exploring is Nomic Embed Text version 1.5. And then as mentioned earlier, we're using things like libpq and pgvector to actually create from within Julia an indexed vector database for future large language model work and research. So to kind of give a quick and dirty kind of where we're at with things right now with the project is that we do actually have a full working prototype that exists within the Julia Health LLM repo. There's actually 2 repos. We'll probably rename one to be less confusing. But the first repo actually contains the material that we want to use for the RAG architecture, whereas Julia Health LLM.jl contains convenience tools and other things specific to the Julia Health ecosystem that can help you develop a local first based large language model RAG architecture setup. So shown on the right is actually a query that was generated using one of these local large language models on my computer using the tools that we've built so far with Julia Health LLM. So as you can see, it kind of does a lot of reasoning and spits out at the end what it thinks is the correct answer. Spoiler alert, unfortunately, that is completely wrong. We are working on revising and optimizing sort of these queries at the moment due to the fact that while we have the tools in place, there is still much room on the table for improvements to be done, such as thinking around Julia's strengths. Julia is great for high performance and well suited for domain specific tasks. But unfortunately right now, things like fine tuning APIs to work with different sorts of LLMs. It's unfortunately quite lacking, so we're working around those barriers right now as we speak to optimize and make these sort of pipelines even better within the Julia ecosystem. And as I mentioned, there's different ways we can improve RAG accuracy and curation around what we actually are putting into our RAG-based architecture. And the final thing that I want to mention is that we're also very much considering exploring safety guardrails around the different sorts of applications taking place. I want to highlight in specifically NVIDIA NeMo guardrails, which comes from NVIDIA, which is their kind of cutting edge research into guardrail technology. And the whole reason why we care about guardrails is that we want to look at how we can ensure safe and accurate LLM language outputs, especially if we're looking at health-related sort of concerns and health-related problems here. And in NVIDIA NeMo, actually it operates as a server client such that we could write a Julia wrapper around this, house this within the Julia Gen AI ecosystem, and still bring the work being done in guardrail and AI safety and surveillance safeguarding technologies to the Julia landscape and ecosystem. So that's a bit of a high-level rough overview of what we're looking at for Julia Health LLM, how we're thinking about approaching bringing large language models into the Julia Health ecosystem, and how we can continue to grow and look at opportunities here with this emerging technology. So thank you all so much for your time, and happy to take any questions. And again, this is the majority done by Param Thakkar, so if you want to reach out to him, he will be the person that could answer more questions if you have them. Thank you. I think we're actually mostly all done for the day, so that's the end of the Julia Health Mini Symposium. So if there is any additional questions, we can float around. Otherwise, that is it. So thank you for the first ever Julia Health Mini Symposium, everyone. Thank you. Hey, Anish. Thanks for presenting. Thanks for presenting. Yeah, of course, of course. Yeah, absolutely. Oh, Andrew, I'll grab you in a second. I'm just gonna wrap up. Yeah. Absolutely. Let's see. So, and definitely would love to connect and chat more about like what you've been up to, what you've been working on. I had questions about what you were doing, but we just ran out of time. So.